The Landslide Scientific Assessment Conference in 2022 provided an engaging virtual experience, streaming live over 3 days via YouTube and Facebook. Focused on the theme of landslide hazard, the meticulously planned schedule ran as follows. Day 1, October 18, 2022, lasted 7 hours, 30 minutes, and 25 seconds. Day 2, October 19, 2022, extended for 9 hours, 45 minutes, and 53 seconds. Day 3, October 20th, 2022, continued for 8 hours, 59 minutes, and 5 seconds. The event was open and free for participants.
Welcome to the Landslide Scientific Assessment Conference. This is the story of LandScient, and for that, I will need to tell my own story as researcher. My name is Roberto Marin, born nearly 33 years ago in Medellin, Colombia. Without any initial interest in a research career, I pursued civil engineering at the University of Antioquia, one of Colombia's top public universities. My first exposure to landslides came during a college course taught by Professor Edwin Garcia, but at the time, my focus was on structural modeling, so I completed the course on slope stability without much extra engagement. However, Professor Garcia later invited us to an extracurricular course on landslides, led by Hernán Martínez, a Colombian professor from Brazil. This course piqued my interest in landslides for the first time. During the course, Edir Aristizabal presented a physics-based model for shallow landslides, which left a strong impression. I didn't realize then that he would become Colombia's top landslide researcher. Not long after that, in another college course, Professor Juan Pablo Osorio asked us to create a research proposal, and I chose landslides as my topic. My proposal focused on how vegetation affects slope stability using physics-based models. In the following semester, I began my undergraduate research project co-advised by Dr. Juan Pablo Osorio. Alongside a fellow student, Juan David Castro, we conducted research that resulted in awards and invitations to scientific events. Our work led to 3 published research articles. The pivotal moment in my research career came after graduation, while I was still working on publishing our results. I was offered a teaching position at the University of Antioquia for the numerical methods course at age 24. This role pushed me to refine my programming skills, which became essential for both teaching and my research. Around this time, I also started collaborating with Edir Aristizabal and Edwin Garcia, who were keen on my knowledge of the triggers physics-based model. Together, we researched the performance of triggers in a Colombian Andean basin, though it took nearly 4 years to publish our results. During this period, I came across a research article by Dr. Massimiliano Albioli on rainfall thresholds for landslides using triggers, which inspired me to delve deeper into the topic. While working with the early warning system of the Valle de Aburrá, a region that includes Medellin, I developed my first program to define rainfall thresholds for shallow landslides, using triggers and Python. At the same time, I began my master's in engineering at the University of Antioquia. In my first semester, I took a landslide hazard course with Professors Hernán Martínez and Edwin Garcia, who also invited Dr. Edir Aristizabal for a session. The course required us to conduct a real-world landslide risk assessment, for which I developed a Python code that used triggers to run thousands of simulations and perform a probabilistic analysis via Monte Carlo simulation. This research became my 4th published article, co-authored with Dr. Martinez and Dr. Garcia. This project also marked my first collaboration with undergraduate students, which was a rewarding experience. I honestly had low expectations of their contribution, but the fact that it was significantly impacting their lives and a real contribution to what was my research became one of the most satisfactory activities in my career. Additionally, we published multiple articles together, many in Q1 journals. This collaboration eventually led to the formation of the Semillero de Investigación LandScient, or the LandScient Research Incubator. In 2017, I was invited to join a large project led by the National University of Colombia to create landslide hazard maps for 7 municipalities in Antioquia. I led a team in applying physics-based modeling with triggers and performed a probabilistic assessment using the first-order second-moment method. Some of the findings were published with Dr. Edwin Garcia as the principal investigator. After completing this project, I was invited by a geotechnical firm to use similar methods for other regions. I led a team in preparing official landslide hazard maps for local governments. Around this time, after finishing my master's degree and continuing as a lecturer, I published my first implementation of physics-based models for defining rainfall thresholds and began my doctoral studies. In 2020, I faced one of the most significant challenges in my life. After leading several important research projects, I decided, with the support of my brother Julian Camilo Marin Sanchez, to officially found LandScient as a company. Initially, I planned to offer the same services I had been providing as a professional, but under my own company's name. However, things did not go exactly as planned. At that time, my primary focus wasn't on building LandScient, even though it was legally established in Medellin in 2020. I was a PhD student, a lecturer, and a researcher leader, and lacked entrepreneurial experience. I knew that LandScient was more of a long-term project. In the same year, I married my wonderful wife, Paola, and took on new projects, including creating landslide hazard maps, still as Roberto J. Marin, not under LandScient. One of the most profound lessons I learned from my father is that every organization must have a clear, significant purpose. Through my experience working on landslide hazard projects for urban planning and early warning systems, I realized that my research and work should focus on saving lives. This became LandScient's mission, to align our work with the goal of saving lives. This is why we always emphasize be LandScient, save lives. Despite creating our website and establishing important contacts, my main priority remained to complete my PhD. I faced considerable financial challenges, so much so that I couldn't afford my third and fourth semesters. But my marriage approaching, I experienced God's miraculous provision, allowing me to complete my studies in record time. Although financial constraints pushed me to graduate quickly, I met all the requirements for the doctoral program by publishing 7 Q1 research articles, 6 of which were published before graduation. I completed my PhD in just 2 years, with my dissertation reviewed by international experts like Maximiliano Bordoni and Roberto Valentino, who are both speakers at this conference. Honestly, it was not just publishing Q1 articles that helped me achieve these milestones. It was God opening doors I never could have opened myself. One of the most challenging projects of my PhD was the development of the software LandScient EWS in collaboration with Julian Camilo Marin Sanchez. Though this research wasn't published in a Q1 journal, and only this year I managed to publish it, It was one of the hardest research challenges I faced during my career. After getting married, I dedicated even more time to humanitarian and mission service activities, temporarily setting aside my research and my organization, LandScient. During this period, I continued as a lecturer at the University of Antioquia, a role I was able to maintain even after moving to a new city in Colombia due to the shift to online classes during the COVID pandemic. This new city, Manizales, became the center of my next research challenges. I approached Dr. Janet Zambrano, the director of the city's early warning system, managed by the National University of Colombia, Manizales campus. There, I once again worked on national hazard maps and defining rainfall thresholds, now with a deeper appreciation for the importance of saving lives in everything I do. As I had already earned my doctorate and my wife and I had plans to continue learning abroad, I began applying for research positions in universities and research institutions worldwide. I was offered a position at University College Dublin in Ireland, where I worked for a little over a year on a project developing deterioration models for earthwork slopes. My supervisor, Mike Long, one of the most prominent geotechnical experts in Ireland, has made significant contributions to the field of geotechnical engineering. He is also a speaker at this Landslide Scientific Assessment Conference and will provide more insight into our important project in Ireland. Together, we co-authored 3 research articles, 2 of which have already been published in Q1 international scientific journals. Before moving to Ireland, I decided to organize an online free and open event about landslides. However, my lack of experience meant I prepared for it with only 3 months of planning, and the event coincided with my move to a new country far from my homeland, Colombia. On the same day I arrived in Dublin, I hosted the Landslide Scientific Assessment Conference, Landslide Hazard, in October 2022. Despite the challenges, the event featured many renowned landslide experts whose excellent presentations contributed to its success. Nearly 800 people registered. In 2024, I completed my work on the project in Ireland and chose to volunteer in Egypt, serving Sudanese people displaced by the war. I have been blessed by God to continue publishing research articles, serving as a reviewer for leading international scientific journals, and now organizing the most significant event in LandScience history. Thank you to all of you, honorable speakers, scientific authors, professors, risk managers, practitioners, professionals, and students. Together, we can all contribute to making this world a better place. It is an honor to chair this event, and, as with many responsibilities I've taken on in life, my main goal remains to save lives. There are countless ways to contribute, so I invite you all to present your scientific advancements, experiences, and knowledge. My message to you: be LandScient, save lives. Yes. Hello, everyone. Welcome to the Landslide Scientific Assessment Conference, Day 2. I am very pleased to be part of this event, to be part of the uh, history of land science. Today, with uh, a wonderful list of speakers, scientific authors, experts in landslides, and we are going to start immediately because I am here right now with Dr. Luca Picciolo. It is an honor for us to have you here. Dr. Luca, how are you?
Thanks. All good here. Yeah, it's starting to be cold in Oslo, in Norway.
Oh, yes. Okay. Uh, Please feel free to start with your presentation. Maybe, as I have asked other speakers, can you just introduce yourself and tell us a little bit? And you can start with your presentation. Thank you so much for accepting
Sure.
this invitation.
Give me a feedback if you see the moving of the text on the photo.
Yes, sir.
Please.
Yes.
Okay, I start telling that
Yes.
I'm gonna hopefully stay in time since we have started a bit in late. So the topic is about an operational IoT-based real-time slope stability forecast using a digital twin. My name is Luca Picciullo. Often I have the joke of the peach to remember my surname, the fruit, the peach. So it's Picciullo, but I decided to skip it, the photo, but I'm telling you anyway, the way to remember it. So I am a senior researcher at the Norwegian Geotechnical Institute here in Norway, even if I'm Italian. I'm also holding now an adjunct professorship position as associate professor at Oslo Met, the Metropolitan University here in Oslo, where we are having a geotechnical master course from this year. So let's start and moving forward in this topic. First of all, I'm going to describe a case study, and I'm going to tell you that this case study started in 2016 with sensors being installed, and this was a site where they wanted to expand the railway line, to double the line. Then a first conference paper was published in 2018. Then I took over as a work package leader in this project called Klima 2050. And then with the help of other colleagues, we wrote a publication about the modeling of this slope. And then recently, thanks to the help of, this case study has been part of an EU project called the HUT. And now, like 10 days ago, this paper has been finally published that describe the operational system and how we are doing this real-time slope stability forecast using a digital twin. And this is the topic for today. What's the aim then? Is to use real-time hydrological monitoring, available meteorological and hydrogeological data, and doing hydrological and geotechnical modeling, and use data-driven machine learning models to forecast the stability of this slope in real time. And this case study, it shows, and it's a first attempt to integrate different critical aspects into an automatic Internet of Things based local LandScient early warning system. So first of all, what is Internet of Things in the context of warning and landslide warning is the use of different sensors that are hopefully strategically placed in the landslide area to collect data in real time and to make this data available for analysis and interpretation, and then to use this data in real time to issue alerts and warnings. So this is a definition of how we can use IoT in the context of landslide warning. And then I want to spend one slide actually on structure of a landslide early warning system. There are different contributions in literature where different authors and papers have schematized the main components of Landslide early warning system. Here is a small review. What is important, and I want to highlight here, is that there are these 5 aspects that or components that are recurrent in these papers, and these are monitoring, modeling, forecasting, warning, and response. So we see here that Landslide early warning system is not only including technical aspects, but also social aspects. So keeping the same main components here, we have proposed a framework of main phases to develop an IoT-based slope stability modeling and forecast, and also to provide warning. So here we are kind of defining what to do in the different main components of a Landslide early warning system. You need to monitor some variables, hydrological variables, climate variables. You need to have parameters, soil, vegetation, hydraulic parameters. You need to build your model, calibrate it, validate it. So you need to build both hydrological model and the slope stability model, and then perhaps you may need some machine learning algorithm to kind of and then use the data and get the information for forecasting climate variables, and then perhaps defining the conditions leading to failure and predict if the slope is going to fail or not, and issue warnings, and eventually finally emergency plan. Let's see how we have practically applied this kind of this framework to a case study in Norway. This is the slope, as you can see in the photo, heavily vegetated. This case study has not shown any deformation. Possible movement is a rotational or translational landslide, mostly silt slide, flow slide, according to Hung classification. The possible velocity is rapid to very rapid. So this is the area, this is the monitored area, this is the railway line at the toe of the slope. This is the location of the sensors. I'm going to tell you what type of sensors we have in a minute. But here I want to point out that we have done some in situ geotechnical investigations carrying out CPTU. And here you can clearly see that the top, this is from the top of the slope. You can clearly see that the first 10 meters are like coarser material, and then below is more firm marine clay. And then we have characterized the upper part of the slope. Since it's in the partially saturated conditions, we have built, we've done pressure plate tests, and then we have interpolated the results using the Wangen-Newton equation. And then on the right, you can see what are the geotechnical parameters that we have used for the analysis. Then this is the practical IoT structure that we have used to build our real-time slope stability forecast model. So we are monitoring something. We are monitoring for water pressure and water content and other atmospheric variables. All these data are collected in real time in the NGI Live. NGI Live is a web platform collecting data and making the data available for analysis. So our digital twin is getting data from NGI Live, running the analysis, and then sending back the results of the analysis in NGI Live, and then we are showing these results. So we have built a model. So this is a modeling of the slope. And this is within this digital twin. Then we are getting information on the forecasted meteorological variables that goes into the digital twin. And then we run our model, and then we are able to publish the results and issue warnings if threshold values are exceeded. Threshold value of both factor of safety and on the hydrological variables we are monitoring. So water pressure and volumetric water content. So how the cloud service is deployed. So this digital twin is a cloud service. and is forecasting the slope stability for the upcoming 3 days. So every day it does the forecast for the upcoming 3 days. Azure functions are used to deploy this cloud service, and it's automatically triggered every day. And then we use Grafana to show as a dashboard to show the results. Let's see how much time I have, and I'm going to show you also the how the dashboard looks like. Now I want to spend at least a minute describing what our digital twin is and what is needed to make a forecast. So we are monitoring meteorological and hydrological variables in real time. We have used the data set, the historical data set, to build a model of the slope and with GeoStudio. And then we have computed the factor of safety. We have used machine learning data-driven models, considering the monitored data as features and the factor of safety as target. We have trained the machine learning data-driven models, two models, polynomial regression and random forest, to compute the factor of safety. And then we are using forecasted meteorological and hydrological data that goes into the trained machine learning data-driven models, and then we are able to make the forecasts of the factor of safety and the hydrological variables for the upcoming three days. So this is how it's structured. I need to remove the pointer, otherwise it doesn't work. So the monitoring, let's talk about what are we monitoring. We have piezometers installed. You see them in blue here on the left. Only the first one is of interest because in the fluctuation area of the water table. Then we have water content sensors installed in the partially saturated area. And then we have a small meteorological station for different climate variables. Here is the slope, is pretty steep in the upper part, 45 degrees, heavily vegetated, as you can see. And this is the sensors, tools, and data loggers we have on top of the slope. Then we have done the modeling. So we have built this model using a coupling SIP, transient, and slope for 1 year period on a daily basis analysis. And using as input for this 1 year of analysis on a daily basis, precipitation, air temperature, snow depth, relative humidity, wind speed, solar radiation and albedo, and also leaf area index, root depth, and vegetation height. So these are the inputs, all the input, meteorological and vegetation, and then we are computing the factor of safety in time. And then we have done a validation. So we have varied parameters, and then we were trying to see which one of the different results from the different models was the best in back calculating what we were monitoring. Usually you see something like this in literature, where you compare the results of your model with what you are observing. In this case, it's the blue line. But honestly, it's very complicated to tell what is the best model to replicate what you are measuring. So I think a better way of doing it is to compare a measured and observed, measured and modeled data is to use Taylor diagrams that they look like that. And they are based on the computation of the correlation coefficient, the normalized standard deviation, the root mean, square difference, and the bias. So we have done that. We have checked which one was the best model to use. Then we have further improved our results, carrying out a sensitivity analysis of the hydraulic conductivity, specifically of the anisotropy of the hydraulic conductivity in the two directions, and also on varying the value of the saturated horizontal hydraulic conductivity for the 3 different layers. And then I don't have so much time. I don't have time to go into details here, but you can check the publication to learn more about how we have done these things and how we have built our reliable model or a model that we trust. And this is the results of the best model. In blue, you see the observed, the measured value of the water content at the 6 different depths. And in orange is the results of our back calculation. This is 1 year of analysis. And then this is the pore water pressure at 6-meter depth, where we have the fluctuation of the water table. Then this is the results in terms of factor of safety in time on a daily basis. Then what else we have done? We couldn't use the GeoStudio on the flight in the cloud. So to bypass that, we have trained data-driven machine learning models. So we are running in the cloud in real time the machine learning data-driven models. Now, these models have been based on these 5 one-year databases, 3 from past scenarios and 2 using future scenarios. The meteorological and vegetation variables are the same that I told you before that we used in the first model that we set up. So we have used it, and then we have computed the factor of safety. So in this way, we had a larger database that was used to train our machine learning models. Then the variables are these 10 features, hydrological variables and meteorological variables. The target was the factor of safety. We tested different machine learning models, but we ended up picking 2, polynomial regression and random forest. Then we divided the data set in 3 different groups, having 4 one-year data set as training and 1 to predict, and varying the predicting one, basically. So what we did, we basically took these 4 one-year databases. Then we were training our model, and then we were validating the model using a never seen one-year data set. And then we ended up defining which one was the best group to use to predict the factor of safety with the polynomial regression data-driven model and with the random forest. So for the polynomial regression was group 3. So, and here you can see how on the left you see the factor of safety modeled using the polynomial regression, and here is the factor of safety using GeoStudio. So the test dataset and the validation dataset are pretty much aligned on this curve. So there, it means that the model was kind of good in predicting the factor of safety that we were modeling using GeoStudio. So this was with polynomial regression. With random forest, we ended up using the, and you can see that it's the best among the other ones. Now, so we have our trained data-driven models. Then we need to make also forecasts for the volumetric water content and pore water pressure. And to do that, we have used a code which is available online, a Python code, a code called Pasta that is written in Python. And it basically provides a framework for the analysis of time series data in hydrology. It uses transfer functions noise that tries to explain an observed time series, in our case, volumetric water content and pore water pressure, by different observed time series. And the different observed time series that we have used are the ones that are listed here. So we were able to predict our factor of safety. This is how it looks like, the correspondence between the observed and the modeled volumetric water content at 6 different depths and the pore water pressure using pastas, and also our forecast in at the end of every graph. And then, so making a recap on how we are doing this calculation in real time of the factor of safety. Let's imagine that we are here at the time of the run. Then we get the past 365 days of hydrological data and meteorological data that goes into pastas together with the 3 days forecast of meteorological data, and then we are able to predict the volumetric water content at 6 different depths and the pore water pressure, and this goes as input into the pre-trained data-driven machine learning models together with information from temperature, leaf air index, and then we are able to compute the factor of safety for the rolling 3 days. So this is how we have done things. I can quickly show the video if it goes. I'm not able to run the video, unfortunately. Oh yeah, it's running, great. So here you have different tabs. So you can see that the tab is showing the map, and then there is other tabs showing the slope cross section, and then there is another tab showing the digital twin results. So in the digital twin predictions tab, we see the factor of safety for the upcoming 3 days with the 2 different machine learning models. And then you see also the adimensionalized value of the volumetric water content and pore water pressure. So if that value is exceeding 1, then we know that it has the highest observed value in 1 year. And then here we are comparing the pore water pressure and the salt water content with what we are monitoring, with what we are modeling, predicting. So prediction is the dotted lines, and continuous line is what we are monitoring. Then conclusions, take away 1 out of 2. We have seen an approach to define a framework to define an IoT-based digital twin, local Landslide early warning systems, and then the importance of using monitored data to back calculate the hydrological condition and to build a model that you trust. And then in this case, we have created a stability forecast that is fully based on hydrological and meteorological condition, not on the formation. So you can know more on this reading the paper. Second takeaway, the possibility of using volumetric water content, pore water pressure, climate variables, and vegetation, I would add, to predict the factor of safety using machine learning data-driven models as proxy of GeoStudio. And then I showed you we were able to define this automatic procedure to compute the factor of safety for the rolling 3 days. And this last point, I think it's important, is this work is a result of a collaborative effort between different expertise like geotechniques, hydrology, meteorology, instrumentation, and informatics. If you want to know more about this last part, this paper has been recently published like 10 days ago, so you can look for the title online and you would find it's open access. Both of them are open access. Thank you very much. This was my presentation. I don't know how it works, if there are questions or not, but let me know. Or you can send me an email if you want to know more, or yeah, thanks.
There. Yes. Thank you. Hello. Thank you, Dr. Luca. I am taking a look at the message.
Yeah.
No questions for now, but it was a great presentation. It is what I am reading here. And congratulations on this very recent publication and what research articles and what you shared with us today. It is amazing. Thank you so much.
Thanks for organizing this free virtual conference. Thank you.
We are back, and I am very happy. I am right now with Dr. Subham Das. Thank you so much for accepting the invitation to participate at the Landslide Scientific Assessment Conference. How are you, Doctor?
Yes, thank you, sir. So before I start, I would like to thank you, Dr. Roberto Marin, for organizing this 2024 Landslide Scientific Assessment Conference. And I would also like to thank you all the presenters and participants who has joined in this event. So myself, Shubham Das, I am a research scholar of ACSIR at CSIR Central Building Research Institute, Roorkee. And thank you for giving me the opportunity to talk on a topic titled Stability and Hazard Assessment of the Progressive Zero Landslide in the Kalimpong region of Darjeeling, Himalaya. So as you all know, landslides are quite frequent around the world, and every year this recurrent hazard causes extensive damage in terms of loss of life and property. So if you see this global fatal landslide database compiled by Frode and Professor Petle, it is clearly indicated that almost all countries around the world have or has experienced fatal landslides. And these fatal landslides caused around 18,000 deaths, and in which India and China are the most affected one. In which India solely shares 18% fatalities in the global database. In India, particularly the Himalayan terrain is more susceptible for landslides. If you see this figure, it shows the normalized kernel density of past landslides occurred in Himalaya. So it is shown that the Western Himalaya and the Eastern Himalayan parts are the major hotspot zone of landslides. So for today's presentation, I choose a landslide located in Darjeeling, Himalaya, and I will present a detailed investigation of this landslide. So in Darjeeling, Himalaya, landslides are quite frequent. So this table shows the past landslide events that occurred in Darjeeling, Himalaya. So if you see this table, it is clear that the rainfall is one of the major landslide trigger in this part of Himalaya, followed by some occasional earthquakes. So in which this 1968 event is the most devastating one. So this figure shows the post-event figures of 1968 event. You can see that the thousands of landslides are triggered in this Darjeeling, Himalaya. So if you also see this district survey report, it is clear that most of the area is come under very high to high susceptible zone. So despite the landslides are quite frequent in Himalaya, there are certain challenges that often limits us their detailed investigation. So these challenges include the sudden occurrence of landslides, followed by, if you compare the frequency of landslides with other natural hazards, let's say flood and earthquakes, it is evident that the high frequency of landslides stands as a practical problem. Other than this, if you compare the return period of landslides, it may be range from annual to seasonal, whereas in case of flood and earthquake, it may be 10 years to 500 years. Next challenge is the size or magnitude of landslide. So in case of landslide, it can be range from a single rockfall to the collapse of the entire hill slope. So whatever modeling one have to done, it should be addressed these both size categories. Other than this, these two figures clearly indicate that the risks of landslide particularly depends on its location rather than its size. Okay, the next is the material involved in the landslide process. So it can be ranged from a microscopic silt to a large boulder. Following this, the landslide can be triggered by both rainfall and earthquake. So particularly during rainfall, increased pore water pressure caused hydrological loading, and this hydrological loading reduced along the potential slip surface and ultimately triggers landslide. Whereas in case of earthquake, this shaking induced dynamic loading causes hillstorm weakening and ultimately leads to landslide. And the other one is the temporal dynamics of landslides. So it is evident that a landslide may be stabilized after the initial trigger, or maybe get reactivated when So therefore, static assessment of existing landslide is very important to the hazard level. So considering the this can be in special level we use GIS technology. In case of high discipline level, we do field investigation in terms of geophysical investigation. More extensive or probability of landslide. And with this kind of probability and know the element of risk, we can easily estimate the risk level. And once we know that, we can go for mitigation and monitoring things. So for this presentation, I will show detailed investigation of landslide. That is in Darjeeling. And with this objective, geological and description of the landslide site, and present the field observation and temporal dynamics of the zero landslide, followed by the analysis that has been carried out for this site, and lastly the stability assessment. And based on this, I will finally conclude with mission and scope of research. So this particular shows the methodology of Darjeeling city in Himalaya. It is clearly evident that this is a company. It indicates the location of the zero landslide. So one may be confused that why it is zero in Darjeeling named as zero.
In transition. Unfortunately, we have problems with the internet connection. I am waiting if Dr. Swam connects again.
I think there is some network issue is there.
Yes, you can share again your screen, please.
Okay, so please tell me where this connection was interrupted.
Yes, it was disconnected, and the audio.
Shall I start, sir?
Yes, sir. Go ahead.
Okay. So sorry for the interruption. So basically, this is the subsurface geology map of this Kalimpong, Darjeeling, Himalaya. So this basically shows that this is the location of the zero landslide, where the subsurface geology is mainly comprises of paro gneiss type of rock. Okay. So, and if you see, this landslide is closely associated with this thrust zone, and geologically such areas are described as weak zone, and when they are subjected to triggering factors, landslides are generally occurred. So if you see the rainfall data that was collected from a local station nearby this landslide, it is clearly indicated that the 80 to 85% of annual rainfall occurred during the monsoon period. So such high intensity rainfall frequently triggered landslides in this Himalaya, in this part of Himalaya. So this slide shows the geomorphological characteristics of the landslide site, particularly the figure number A and B. So figure A shows the elevation map of this area, and this black mark shows the landslide polygon mark. Okay. So from the elevation map, it is clear that there is a high elevation contrast is there in the landslide site. Similarly, if you see the figure number B, the slope of this area is highly steep, and such geomorphological configuration often favors landslide. Other than this, if you see the figure number C, it is shows the temporal traces of landslide. So it is started in 2014, and the satellite data sets we have collected up to 2022, and within this date the traces of landslides are marked here. So from these traces, it is clearly evident that a retrogressive progression is there, and this landslide is threatening the upslope settlements and roads. So this figure particularly shows this field photograph of this landslide. So you can see that in the crown section, a school building is there, followed by a Nimbong village is there, and other downslope roads are there. And all these risk elements are highly threatened by this landslide. And this figure shows the field photographs. At the crown section, you can see that the tension cracks are there. You can also see that the earlier roads are damaged, and the exposed rock structures are in very poor condition. And this analysis shows the NDVI based analysis. So by interviewing locals, I know that this landslide was first occurred in 16 July 2014. So this same thing can also be observed from this NDVI result. If you see that prior to the failure, these values are in higher side, and once this failure occurred, this high variation can be observed. Okay. So following this, I also did a INSAR-based analysis for this landslide, and for this I used SBUS INSAR method. And for this SBUS INSAR analysis, I used Hype3 and MinPy processing platforms developed by Injune 2019. So this figure shows the methodological flowchart used for SBUS INSAR analysis. It started with downloading Sentinel-1 SLC images up to the velocity estimation. And this figure shows the average spatial coherence captured by Sentinel-1 SLC images. So you can see that the spatial coherence values are typically low for this area. So this may be due to the presence of dense vegetation in this area, which often occurred due to the diffuse scattering of microwave waves. And this figure shows the interferogram network for Sentinel-1 ascending and descending orbit directions. And this shows the SBUS INSAR derive line of sight velocity estimation for the ascending and descending orbit direction. So these results actually come in 40 meter by 40 meter pixel format, but for representation purpose, I used this point format. So it is clearly evident that the movement is there in this landslide. And if you see at the crown section, near the crown section of this landslide, high movement can be observed. And this slide shows the time series distribution, time series line of sight velocity estimation along the ascending and descending orbit directions. So for the ascending orbit, I obtained a maximum velocity of negative minus 8.21 semi per year, and for the descending orbit, the velocity was around negative 11.5 semi per year. So following the SBUS INSAR analysis, I also estimate the velocity and volume of this zero landslide. So for velocity estimation, I used a empirical method, and to show this, I use this figure for example purpose. This is a famous Kaliasur landslide in Uttarakhand, Himalaya. So let's assume I have this slope, and you can easily determine the height, length, and the energy line of this slope, either using digital elevation model or field measurement. And if you put a block here, due to the action of gravity, this block will slide down. So Seidegger used this concept and proposed this equation to estimate the landslide velocity along the runout path. So by applying this equation, I obtained this velocity profile for the zero landslide, which indicates a maximum velocity of 21 meter per second. But I think this velocity is overestimated due to non-consideration of bed frictional resistance. Yet, but this can give a faster information. Other than this, I also used this ellipsoidal method proposed by Crew 26 to estimate the landslide volume. The operators are in the form of fifth order of magnitude. Okay, following this, I did the stability assessment. So for stability assessment, I used this finite element modeling. So this shows the configured slope profile where element noded triangular finite element mesh is used and appropriate boundary conditions are applied. And to define the material, we field study and also did some lab investigation, and based on this we get a critical factor of safety value of 1.07 for dry condition and a unstable value of 0.78 for wet condition. To generate the wet condition, RU pore water pressure coefficient, which clearly indicates during the rainfall exposure. So based on this attempt, our key findings are that the crown section of this landslide have a high chance of failure in near future. Therefore, design and implementation are required to further loss. So based on this study, there are some limitations are there, which can be also incorporated as an aim for future research. This include the present analysis mainly. So we have did direction test and get specified value, and we use it for our numerical. But Luca shows some CPTU's values you can see in his presentation, the earlier presentation. So such uncertainties can be easily incorporated using this probabilistic analysis. Other than this, we can also consider these uncertainties in terms of spatial variability, that these properties can be vary both horizontally and vertically. And lastly, the most important thing is the designing the stability measures and perform the coupled seepage stability analysis to get the more realistic results. And these are the references that I used during this presentation. And these are the two publications related to this presentation. And thank you.
Thank you so
Hello.
much, Dr. Subhamdad. Thank you for.
Sir, yeah, I am still Mr. Doctor. I am still pursuing PhD.
Okay, okay. Thank you for sharing your research.
I really sorry for the interruption. This internet connection was interrupted.
Okay. Thank you. Thank you. We are going to click video entrance. Yes. So I think no questions for now.
Okay.
Thank you. It is actually on. Okay, we are back, and we are here with Dr. Rosa M. Palau. Thank you so much for accepting our invitation, a direct invitation to be part of the Landslide Scientific Assessment Conference. And welcome. How are you?
I'm very good, thank you. How are you?
I am very good, thank God. So feel free to present us what you prepared, but maybe as I have asked other speakers, can you please very briefly tell us about yourself, to introduce yourself, and you can continue with your presentation.
Yeah.
Thank you so much.
Sure. Hi, I'm Rosa, and I'm currently working at NGI as a researcher. And the presentation I'm going to do now is about part of my PhD thesis that I did before coming to NGI to be a postdoc before now, 3 years ago. And it's about a landslide early warning system use of hydrometeorological thresholds. So yeah, it's a result from my thesis that I did at UPC in Barcelona, but that I'm presenting now from NGI. And also everything that I will be presenting, it's published in a paper. So if you are interested, you can also go and check and learn more about it. So, okay. So as we know, landslides are an important hazard that affect areas in mountains in the world. And even though it's not as known in Spain to be a hazard, we still have some landslides. And also because of climate change, we see that we have them with a higher frequency, and they also impact infrastructures and buildings, and they represent issues for a population that live in the areas that are affected by them. So what we need to do and what we want to do is to create ways of decreasing the risk, and we need those tools to decrease the risk, and so that emergency managers and people that live in the areas that might be affected can be aware of the hazard and take actions. So the landslide early warning system for Catalonia, this is what I developed during my PhD thesis, uses radar rainfall information as an input. Then it computes the hazard in the warning on a subbasal level. And if you are interested, you can zoom in because the warning levels are actually computed on a 30-meter pixels. So you can zoom in into the area you're interested and observe what's going on. And here you have some results of the landslide warning system working for an extreme event that occurred in Catalonia in January 2020, where multiple landslides were triggered. And as you can see, we get that this warning level increases in the areas that are affected by more precipitation. Yep. So as I said, the original version of this landslide early warning system used only radar rainfall observations to compute the warnings over Catalonia. But what we want to do, a problem is that soil moisture is very important, and we know, but mostly it's not taking into account into regional scale landslide early warning systems. So what we did was combining susceptibility and rainfall and obtained a warning map. But what we thought is, can we improve the landslide early warning system performance if we, instead of using only rainfall information, use also information regarding soil moisture? So what we did was including soil moisture as an additional input. And then instead of using rainfall thresholds, as we had been using before, we replaced them by hydrometeorological thresholds that combine rainfall and soil moisture information. Then we obtained the hydrometeorological hazard over the entire Catalonia. And then that was the thing that was combined with susceptibility to obtain a warning map. that would be updated every time we got new rainfall and soil moisture information. So when we started this to work on that, we thought, okay, we need soil moisture data over all Catalonia. And that was a challenge because if you can see in this map, and that's the soil moisture sensor network existing in Catalonia. And it's only a few sensors located in the northwest. And we know that this is not good enough for the entire region because the soil moisture that those sensors would measure up there in the northwestern Pyrenees is not representative of what's the soil moisture over all Catalonia. So we decided that this was not the best option for our case. Another option would have been using satellite soil moisture information, and we considered that, but we also thought that, okay, we want to run this landslide early warning system. This is running operationally in real time. So what we need is to have this information in real time. And the case with satellite products is that most often they come with some time latency. So you don't have the soil moisture the day that the soil moisture is observed, but you have it a few days after. And this is not interesting for us, which we wanted to have this on real time operational. So instead of satellite, we decided that our way to go would be using the output of hydrological models, which we have distributed hydrological models covering the area. And we decided to use the list flood model, and we used the runs from the EFAS, which is the European Flood Forecasting System. So we have this soil volumetric water content, which is modeled by list flood, covering all Europe. And then we have daily outputs, and they have a 5-kilometer resolution. And here in these two maps, you can see the volumetric water content over Catalonia to 2 days. No, it's the same day. Okay, the same day. And we can see that we have a spatial variation of the soil moisture in areas in the north and in the south, with areas with more moisture, volumetric water content than others. Yep. Then we analyzed this, and here we see that over time, for a period from 2018 to 2020, and here we have the percentiles of volumetric water content conditions in Catalonia. So in the left, you can see the 25th percentile, and in the right, you can see the 75th percentile. As you can see, the areas that are more that have higher soil moisture are located in the Pyrenees, and they are usually areas where it rains more, and so they are more wet. And towards the southwest, we have areas which are a bit more dry, and therefore it's lower water content on the soil. So after analyzing all this, we decided to obtain these hydrometeorological thresholds. So what we thought is, okay, we will include volumetric water content as a third dimension into the intensity duration space. So here we can see the intensity duration thresholds that the landslide early warning system was using. And what we did is include a third axis, which would be volumetric water content. So then if we look at this volumetric water content, we could summarize it for the intensity duration for the given duration, like in for the equivalent intensity given a duration. So here we have the equivalent intensity volumetric water content axis, which would be the intensity for half an hour durations, which is what we chose to use. And then in this space, equivalent intensity volumetric water content axis, we can see that the thresholds are no longer logarithmic, and we have that the thresholds are constant lines in this space, and we can summarize basically any rainfall intensity for its duration, for the equivalent intensity for a given duration for half an hour, because those intensity duration thresholds are based on IDF curves for which we know the equation. So here we have a rainfall event that might trigger a landslide. And what we did is, okay, as I said, we represent this for the half-an-hour equivalent intensity, and then we can plot it in this space so we can see where it is in this volumetric water content space. And we can draw a threshold which takes into account the volumetric water content to separate between landslide events and landslide no events. And that's what we want to do. So we needed landslide data and no landslide data. And this is the information we were working with. This is the landslide inventory that we had. And it consisted of 603 landslides over Catalonia. Most of these landslides were reported during some significant rainfall events that triggered many landslides. And so yeah, and we were working with this. So if we plot all these rainfalls that triggered the landslides, which are in blue, and the rainfalls that did not trigger landslides, which are the gray diamonds, in the equivalent intensity volumetric water content space, this is how the data looks like. And at the first glance, it's not easy to find those thresholds. But we wanted to find those thresholds. So what we did is we obtained these thresholds heuristically, considering this combination of these volumetric water content equivalent intensity thresholds, rainfall, hydrometeorological hazard, with susceptibility. And what we expected is, and what we can see in this last slide, is that we have more landslides when the volumetric water content is low, if the intensity is high. But if we have a higher volumetric water content, we have more landslides, even if the intensity is low. And that's what we expected. So these thresholds, as you can see, are higher if are higher when require higher intensities to be overcome when the volumetric water content is low, and require lower intensities to be overcome when the volumetric water content is high. And here you can see these thresholds, which are the black lines and the different colors, and the white discontinuous lines in this case represent the old rainfall intensity duration thresholds that we used. So we've got these thresholds and we implemented them into the landslide early warning system, and we run it for the period April to October 2020 with both intensity duration thresholds, and then we run it with the equivalent intensity volumetric water content thresholds that we had just obtained. And here is the warning map summary of the landslide early warning system when we run it with the intensity duration thresholds. What we can see here is the number of days with warning that we had obtained. And if you look over the northeast of Catalonia, close to the border with France, we can see that there are quite a lot of days with landslides. Technically, it's up to more than 30 days with landslides in some sub-basins. But if we look, when we run it with the equivalent intensity volumetric water content thresholds, we see that the number of days for which we predicted landslides were possible are much less. So in this sense, we're saying, okay, these thresholds seem promising and they help us reducing the number of days for which we give warnings. And this was one of the first times in which such type of thresholds were implemented into a landslide early warning system at a regional scale in real time. Then the performance at a regional scale was challenging. So what we did is this analysis, more qualitative. If we looked month by month, we see that the month of June, that was raining a lot. We thought, okay, why did we get so many warnings on the overall period? So if we looked at the month of June, we can see that we had important rainfalls, accumulations in the northeast, and also the volumetric water content was quite high. Oh, this is actually, then if we look at the output with the intensity duration thresholds, we can see that we had some days with more than 9 days with warning in some sub-basins here in the area where it rained more and the volumetric water content conditions were highest. And if we look at the outputs of the landslide early warning system for the month of June, we see that in that area, there were fewer days with warnings, up to 3 to 5 days. So we decreased the number of days with warnings, as I said, quite a lot. But this is not very quantitative verification. So what we did, because we needed more data and we had already used almost all the inventory for the obtention of those thresholds. So what we did is picking up some events for that were even more recent and which we had not used for the calibration of the landslide early warning system, hydrometeorological thresholds. And then we checked if we were making any improvement in this period from April to October 2020. And this is here I'll show you a case, the case of the landslide in Vegas, which is indicated in the susceptibility map in the left-hand side of the slide as A. And here we had a landslide, well, a debris flow that occurred the 21st of April 2020. It was a day with an important rainfall event, quite extreme. And yeah, there was this debris flow. It blocked the road for several hours, I think days even. And it was a problem because there were some municipalities that were in the other side of the road, which was not able to use. So we looked at here we have the rainfall time series from April to December 2020 in blue, and in orange we have the volumetric water content time series from April to December. And what we see here in the color bar is the warning time series using the intensity duration thresholds. And as we can see, when the rainfall, the 21st of April, here, when the landslide occurred, the rainfall that was observed was quite high, and also the volumetric water conditions were high. So with such rainfall intensities, we could predict using the intensity duration thresholds that a landslide would occur. But here is what we get when we run, and then we run it with the hydrometeorological thresholds, and we see the warning time series using these hydrometeorological thresholds. And we see that we also could predict, because the volumetric water conditions were also high, a landslide on that date. But if we looked at, so here we have a true positive. If we look at other September 2026, we see that, 2020, we see that there was a day for which the rainfall intensity was not as high and the volumetric water content was not as high. But with the intensity duration thresholds, we would issue a warning moderate. And with the hydrometeorological thresholds, we would not issue a moderate warning. We would say that the that the landslide possibility of landslides is low. And then another day in December, we had another moderate intensity rainfall event. In this case, the volumetric water content in the terrain was a bit higher. And in this case, both intensity duration thresholds and hydrometeorological thresholds combined with susceptibility gave us a moderate warning. So in both cases, we have a false positives because no landslide was observed. And that we did for all the sites that we saw in the previous slide, and we obtained similar results. So in general, we decreased the number of false positives when using these hydrometeorological thresholds, but still we had some. So yeah, this is the conclusions. We implemented a first version of the hydrometeorological thresholds for Catalonia in the landslide early warning system. We developed them and we proposed them. And we used the volumetric water content from the EFAS runs of the least flood model. This is interesting because it's you can get it in real time, and they run it, and it's for whole Europe. So this idea could be applied to other areas. But to make a more in-depth calibration and validation of these hydrometeorological thresholds, we would need even more landslide inventory covering longer periods of time. That we did not have, so we were very limited into what we were doing to verify that the landslide early warning system was getting the results with these new thresholds. But still, that was one of the first times anyone tried to use such thresholds, and we think it was quite successful and promising. And if you want to know more, it's all published in a paper in Landslide, so you can just scan this QR code and read more about it. That's it. Thank you for your attention.
Thank you. Thank you so much, Dr. Rosa. I'm taking a look to the chat. I don't see questions. If I don't read questions, feel free to all those who are connected via YouTube. You can write your questions in the live chat. But thank you so much, Rosa. It was very interesting. I really love this topic, and I am very glad you shared your research advancements with us today.
Thank you.
I hope to see you also in our next conferences, and thank you for your presentation today.
Thank you.
Okay. Okay. We are back. Hello, everyone. Again, I am honored to present Dr. Susana Pereira. Welcome. How are you?
I'm fine, thank you.
And thank you.
Thank you. I would like to thank the invitation to be here today in this program. Thank you.
Thank you for accepting our direct invitation to present in this event. And it is your time. Maybe I am going to ask you, please introduce yourself. Tell us very briefly about you or your research, and you can continue with your presentation. Thank you.
Okay. Hello, I'm Susana Pereira. I'm an assistant professor at the University of Porto in the Geography department. And today I will present some results of a previous research project funded by the National Portuguese Science for Foundation for Science and Technology. And the title of this work is a landslide risk index for municipal land use planning in Portugal. This was a project of 3 years of research, and I have more colleagues that participated here in this study that are listed here. To begin, to start this presentation, I would like to say that in Portugal, in the last 150 years, landslides caused 237 fatalities and more than 1,600 displaced people. And the spatial distribution and temporal patterns of these landslides can be related with some a complex set of natural factors and also human factors responsible for generating damages. In this context, it is important to develop some methodologies to synthesize risk dimensions and to contribute to risk management. As we can see here in this picture, we have the spatial distribution of the landslide disaster cases and also the information about the elevation of the country, where the steepest areas and the mountain areas are located in the northern sector and also in the center of the country. And these areas are the most prone to landslides. Also, we have some cases of landslides near the Lisbon metropolitan area. And these cases are responsible for a large set of landslide fatalities and also displaced people, as we can see here, where we have two main spots of damages caused by landslides, here in the Lisbon metropolitan area and here in the Oporto metropolitan area, where we have more population and also activities located in hazardous areas. Also, we have some cases of fatalities widespread in the northern area, most of them related with railroads and roads that were affected by landslides and caused fatalities. So in this context, we had published a database of these landslide disaster cases for the period between 1865 and 215, which was updated until 2020, and is available at the Zenodo platform if you want to download and check the data. In this context, the main objectives of this study are to assess the landslide risk using a data set of variables to characterize risk dimensions, for instance, hazard, exposure, and physical vulnerability of buildings. We'll use normalized and weighted variables to compute a landslide risk index that will be represented at the municipal territorial unit. The second objective is to perform a cluster analysis to rank the municipal landslide risk in order to identify landslide risk profiles for different groups of municipalities, and also to to contribute to the identification of different measures adapted to the risk profile of each municipality. When we go to data and methods, we used an adaptation formula of the risk of the informed methodology. Our landslide risk index results from the multiplication of the hazard, exposure, and physical vulnerability of buildings represented at the municipal terrain unit, and the landslide risk dimensions, for instance, hazard, used some variables to assess hazards at the municipal level. For instance, an index that represents weather and climate events that caused disastrous landslides in the past, and also the identification of the most susceptible areas of the country using a bivariate statistical model, the information value. About the exposure, we used information from the Portuguese census of the population from 2010, and in order to obtain information about the population density and the number of buildings. Additionally, in order to estimate the physical vulnerability of buildings, we used the georeference base of buildings of the country, which all the constructed buildings with residential function are located. And then we have some details about these buildings. For instance, the construction technique and construction materials, the building structure, the number of floors, and also the conservation status of those buildings. And so we have this information for the complete country. When we start looking to the hazard and how we did obtain the hazard at the municipal level, we started with the landslide susceptibility map that was obtained from a national landslide susceptibility model. This model used a geomorphological landslide inventory with more than 7,000 landslides widespread in the country, located in some sample areas where we performed field work and photo interpretation, and we were able to identify more than 7,000 landslides. And at the same time, in these 14 selected study areas, we believe that they are representative of the country geology, diversity, and also the geomorphology, the diversity of the country. So we used this inventory based on photo interpretation and field work, where we know that the temporal resolution is low. Most of the times we do not know the dates of the occurrence of these landslides, but the spatial resolution is very, very good because we know the location, and so we can assess the predisposing factors associated with these landslides location. And this inventory corresponds more or less, includes more or less landslides for the period starting in 1950 until 2015. Then we used a set of 7 landslide predisposing factors with a raster data structure with 25 per 25 meters resolution. And we consider the elevation, the slope angle, the topographic position index, the lithology, the soil type, ecological units, and water availability in the country. And then the next step was to perform the bivariate statistical model, the information value method that is represented here with this formula, in order to identify the most susceptible areas in the country. In this case, the areas with the positive information value scores were selected from the landslide susceptibility model and were isolated the most unstable areas of the country, okay? And then the percentage of the municipality area with a positive information value score was computed for each municipality in order to obtain the most susceptible area for each municipality. I forgot to say that this landslide susceptibility model was validation using success and prediction rate curves, comparing with different landslide inventories. And in this case, the success rate of the model that used more than 7,000 landslides was 0.94. So we are very confident with the results of this model in this case, as I said here. And then in the end, the areas with positive information value scores were selected from the landslide susceptibility map, were isolated, and then we computed the most susceptible area for each municipality, and then this information was normalized between a range in the interval between 0 and 1, just like that, in order to identify the most susceptible landslides in the country, most susceptible municipalities in the country. In order to obtain the landslide hazard, we needed a temporal dimension of the landslide triggering, and again represented at the municipal level. And our choice was to perform and to compute a weather and climate event index. And in order to compute this index, we performed a statistical study in order to know the most frequent circulation weather patterns associated with landslide disaster events. We have published this work previously, and we concluded that the landslide disaster events usually are associated with southwestern patterns, western patterns, and also cyclonic patterns, which can be represented at the municipal scale. And also we computed an extreme precipitation susceptibility index that considered high intensity rainfall events. And in this case, we performed a weighting of these parameters, a multi-criteria weighting. And in order to obtain this index of weather and climate events. Again, this weather and climate index is a proxy for the temporal dimension of the hazards, and was computed using the equation proposed by Santos et al. And the results were further normalized again to the interval between 0 and 1. And then we obtained the municipalities where the triggering conditions are more frequent to obtain disastrous landslides. Again, in order to obtain landslide hazard, we combined landslide susceptibility and landslide and weather and climate events responsible for the landslides, attributing more weight to the susceptible conditions, because the predisposing factors that we found in the territory have more control in the landslide location. And then we obtained the hazard representation at the municipal level, again normalized in order to be compared with other indexes. About the exposure, the exercise was very, very simple. We used the population density at the municipal level, and also the number of buildings, because the spatial distribution of landslide losses shows that landslides occur in areas with the highest population density along transportation corridors and in buildings. So the most exposed areas are located inside buildings and along transportation lines. More than 50% of the landslide fatalities occurring in the period between 1865 to 2010 and occurred inside buildings. This is why we only use the buildings. The exposure dimension considers the population density, number of inhabitants per square kilometer in each municipality, and also the number of buildings in each municipality. Both of the variables were obtained from the population census in 2011, and we attributed a same weight for each variable in order to obtain the exposure index in the country, where it has a different spatial distribution, very influenced by the location of the main cities and the main infrastructures of the country. Finally, the physical vulnerability, again, we selected the buildings. Here, the physical vulnerability of the built environment is the degree of loss due to landslides, expressed on a range from 0, no loss, to 1, total loss. We considered 4 building features: the construction materials, the reinforced structure, number of floors, and conservation status, in order to obtain this vulnerability index. For each building feature, we selected a list of building feature classes, we for each building feature class, we attributed a vulnerability score that were attributed based on an empirical weight, based on our field experience, and in the end, the results are consistent with the building's construction quality along the country and with the landslide damages reported in the landslide database for more than 1 century. So the result of this weighting, of course, in the end, we attributed a score for each building feature according to some references and some previous studies that you can see in the final publication of this study. And then the final result was this, representing the physical vulnerability of buildings, where we can find the buildings with lowest construction quality and lowest resistance in the center and in the Alentejo area of the country. The results of the landslide risk, applying the landslide risk index, combining hazard, exposure, and vulnerability, we obtained this landslide risk index for the country at the municipal level, where we can rank the municipalities from the lowest risk to the highest risk in the country. For instance, we can see for each of these municipalities, for instance, Porto, the results of the landslide risk index is, for instance, 0.71. And we have another municipality here in the northwestern part, that is Parede de Coura, with a landslide risk index of 0.61. But if we compare both municipalities, the landslide risk index is high, but the contribution of each landslide, risk dimension is different. In the case of Porto, the most important landslide risk dimension is exposure, as we can see here. And also, of course, we have an important contribution of the hazard index in the municipality. So we have the highest landslide risk index in the area, because we need the combination of these 3 dimensions. In the case of this municipality, Parede de Coura, the most important variable is hazard, but we need to take into account that in the future, if we increase the exposure or if we decrease the physical vulnerability, we can increase our landslide risk index. So this index is important to understand in which risk dimension we should intervene, and we should work with the spatial planning at the municipal level to prevent the rising of the landslide risk. In our case, in Portugal, the landslide risk index has a high correlation between the hazard where we can find a square correlation of 0.91 with the hazard and landslide risk. So the conditions of the terrain and also the triggering conditions are more important than the hazard and the exposure to explain the location of the risk index. The landslide risk index also used these results in order to compute some cluster analysis to identify for each municipalities which are the most important landslide risk drivers. And the landslide risk in different sets of municipality is driven by hazard, for instance, in clusters 1, 2, and 3, by exposure in clusters 4 and 5, and by physical vulnerability of buildings in cluster 6 and cluster 7 that are more important to explain these results. So the landslide risk management strategies at the municipal level must be adjusted to the corresponding dominant drivers of the country and not applied equally in the territory. So the main results of this study let us conclude that if you, according to the landslide risk main drivers in each municipality, if we want to reduce hazards, we should improve nature-based solution, structural measures to increase slope stability also. But if the main problem of our municipality is exposure, we can update and decorate the landslide hazard mapping. We can improve early warning systems and relocation to non-risk areas. Concerning physical vulnerability, if we want to reduce the physical vulnerability, we should adopt building codes that reduce the propensity of physical damages and the loss of goods. Strategy is an important contribution of this work, especially at national and regional scale. Also, we can apply specific risk management measures for each cluster of municipalities according to the particular incidence of each risk driving force. And finally, disaster risk reduction should be developed, providing information for recovery and reconstruction, and also reducing exposure and vulnerability. The maps and the graphs about this landslide risk index are published online, available for consultation in the Forland project, and are available in these links, so you can see it and download it. And also all the study and all the details and the technical details are explained in this publication, published in the Science of the Total Environment in 2022. So thank you for your attention, and if you have questions, please be free to ask. Thank you.
Thank you so much. I don't know what happened, I was disconnected. Thank you so much, Dr. Susana.
Thank you
for your time preparing your presentation, and for everything you did and you presented today.
Okay, if there are some questions, they can send me an email.
Yes, yes, sure. And I can also remind all those who are connected via YouTube, feel free to write questions in the live chat. I am reading right now the chat. Uh, so there are no questions for now. So thank you so much.
Okay, thank you. Bye bye.
Bye bye. we are here back. Phil, very welcome to this your event, the Landslide Scientific Assessment Conference. We just had some problems or issues in the streaming in the previous presentation. I hopefully I think in the Google Meet recording it can be complete or without the issues we had. So probably in the LandScient channel we will have the full presentation without the problems. Or other option is just we will find a way to present you all the results and the research by Susanna, Dr. Susanna. She even sent me a message about it. So we hope that we can share with you the presentation complete without problems. We are here in the schedule. We are waiting for our next speakers. I am still waiting. Let's have some other minutes. If not, there is still another presentation that we have ready. And if during this time the speaker that was scheduled does not connect, so we will just wait some seconds and you will have the next presentation. And we are back, and I am honored to introduce Dr. Marco Yoche. We are happy, very happy, and very pleased that you accepted our direct invitation to be part of the Landslide Scientific Assessment Conference. Please, before you start, and this is your time, tell us about yourself, and then you can start with your presentation. Thank you so much.
So first of all, I would like to thank you, Roberto, for the invitation. And my name is Marco Locke. I am a researcher in the Czech Academy of Sciences. And today I would like to present a work that was started in the Charles University with Gianvito Scaringi that you see in the presentation. And it is about the temperature and the shear rate effects on clays. And this work has been published recently. And the idea is to present the outcomes of the presentation. So first of all, I will present in this structure a simple introduction of some methodology, the results, and the conclusions. And I would like to start the introduction with a question. And the question is why we should study the temperature effect and why they are so important. And one first consideration is that the global warming is affecting the natural equilibria, and this is very important for in the GeoSAP perspective, and in particular for landslides that are the focus of my research, and particularly the frequencies, the magnitude, and the pattern of landslide are changing with the global warming, and usually, to predict these climate change effects, the most common models are accounting the precipitation patterns, and on the other hand, the temperature effects are kind of not studied in detail, unless we are talking about freezing and thawing, and so permafrost environment. However, temperature is very important. Temperature is changing properties like soil strength, compressibility, viscosity, and many others. And from this point of view, we should account for the effect of temperature in slope stability, and we should even think to account temperature for future landslide susceptibility. I mentioned that we are going to study the clay materials, and to give a perspective, the distribution of clay minerals with and above the 25% is covering a large area over the globe. So the scale of our laboratory test and modeling can cover a large area over the globe. And to see in detail what we studied, we can see that we developed two main scales, and we studied two main scales at laboratory scale. We studied the residual with a modified ring shear apparatus, and at slope scale, instead we developed some slope stability model using GeoStudio and creating a subsequentially coupled thermohydro and mechanical model. To do so, we modified the ring shear apparatus to reach the residual and to change the temperature in the water bath. We studied two principal materials that are bentonite and kaolin, so low activity clay and active clay. And we expected to see three principal reaction in the residual: a positive, a negative, and a neutral effect. And we are going to see this in detail in the results that I'm going to plot right now. As you see, the ring shear test that we performed on bentonite and kaolin are presenting very different behaviors. These behaviors are based on different shear rates that are ranging from 0.018 to 44.5 millimeter per minute, are changing based on the normal stresses, and are changing changing the temperature. This is very interesting and even quite complex to study. And to go in detail, I was speaking about the possibility to have positive effects, and you can see in detail, for example, for the bentonite that we studied. And in detail, we can see a positive effect, so a strengthening of the material when we increase the temperature. You can see in the graph, in the right bottom part, the temperature that is increasing from 20 degrees to around 55 degrees. And the response of the shear stress in this bentonite, a very low shear rate, is quite strong and positive. Also, we can see a really nice relationship between the temperature changes, the oscillation of temperature, and the change of the shear stress. And at the same time, we observe a positive effect in the kaolin, but a different shear rate. This is another interesting evaluation. But I mentioned before that we can have also negative effects. And another detail is about the bentonite at shear rate of 0.5 millimeter a minute. And you see that the shear rate is decreasing of 3 points with the increase of temperature, again, from 20 degrees to 55. This is very important because the decrease of shear strength can cause changes in slope stability. Similarly, we observe another weakening in the kaolin, but at different velocity, at the velocity of 0.018 millimeters per minute. Summarizing, we can see that the kaolin and the bentonite, even though are two clay materials, they behave differently. They have a kind of a reverse behavior. This is clearly connected with the mineral properties of the material. And together with this consideration, we should highlight that, for example, the friction coefficient of the bentonite is changing of around 13%, changing from 20 to 50 degrees. This is a quite significant change, and we can think to account this in some slope stability model. And we did this, obviously, and the idea was to firstly to test a simple slope stability model, not accounting the temperature, using the method of the slices, and estimating the slip surface. The slip surface was estimated, and the factor of safety of this precise slip surface is 1.05. So it's a stable slope. However, this model is not accounting any thermal effect that we were studying in the laboratory. So we decided to account our next model with a general sinusoidal thermal signal is given us the possibility to create 4 models for every season. And we can focus, for example, on the summer model, where factor of safety changed and reached 1.08 for the very same slip surface. However, we didn't stop here, but we create other 4 models accounting for the most common global warming scenario, so accounting for an increase of 5 degrees. And interestingly, we observed that the factor of safety of the very same slip surface decrease and reached the unity, making this slope unstable. So to summarize, the modeling part of our paper focus on the consideration that a model not counting the temperature is not potentially predicting properly the stability of a slope under the change of temperature that seasonally are happening, and also we account for the global warming effect, and we observe a decrease in the factor of safety that is quite important. These considerations are related to the residual shear strength, and so are very important for reactivations. Another point of view is it is interesting to see that plotting the factor of safety over the slip surfaces is showing that the majority of the slip surfaces are decreasing their value in the warm seasons that are summer, for example, and the summer that we account with the climate change scenario even more has been affected by the accounting of the thermal friction angle. Now, to summarize and conclude the presentation, I would like to highlight the contribution of this work. And first of all, I think we contributed in covering the gap of knowledge about the thermal effects and slope stability. There are not many papers on the topic. Now they are slowly growing, but when we start this research, the knowledge was really scarce about that. And we contributed in an experimental database because we tested 2 clays, 2 pure clays, and we are planning, we are currently increasing our database about thermal effects and materials. Even more, we demonstrated that the change of safety factor on clay slopes is quite evident, accounting the temperature effects. And to conclude, we think that these are quite simple application, and the experimental-based incorporation of temperature dependency can be easy to account in constitutive models and in modeling. I would like to conclude that these are the references, that these are the contribution. And with this list of publication on the topic, I thank you for your attention, and I'm here for any possible question.
Thank you so much. Sorry for my noise here. It was a wonderful presentation. Let me take a look at the live chat right now. And see. just comment from the some of the previous presentations. So no questions for now. So thank you so much, Dr. Marco. Thank you for your
Thanks a
time.
lot.
Thank you for your big effort, also for um, being ready to present right now. And we are back. I am pleased to welcome Dr. Giambitis Caringi to the Landslide Scientific Assessment Conference. I am honored that you accepted our direct invitation to participate in the event. So it is your time. Please just very briefly before your presentation, introduce yourself to the audience, and thank you so much.
Thank you, Roberto, for this wonderful initiative. Sorry again for the mistake with the timing. I hope I can recover. And so I am Gianvito Scaringi. I am from Italy, but I work at Charles University, Università Karlova in the Czech Republic at the Faculty of Science, at the Institute of Hydrogeology, Engineering, Geology, and Applied Geophysics. My research concerns, of course, landslides, but not only. And the topic I am presenting today actually comes a little bit from farther away, because it is something that I've begun to study since my time at the university, since my master's degree and then my PhD, and it concerns the effects of chemistry, the chemistry, let's say, in clay landslide. What is its effects, its role? Because very often it actually is an overlooked component of the soil behavior. I really love clays because among old soils, they are the most complex, I would say. So clays are hydrated phyllosilicate minerals. They have a complex structure inside. They are basically made of a succession of sheets of tetrahedral silica and octahedral alumina, and depending on the way this layer, this very thin layer, we are at Armstrong's size, thickness, depending on the way these layers are stacked, you can obtain different clay minerals, and these different clay minerals actually have completely different properties. You can go from quite compact stacks which do not even have much activity, they are very stiff, very hard, like those of chlorite, to different structures that can, let's say, exhibit a plastic behavior, interact with water in various ways. You go from normally as interesting clays, which are also the most common. We study the group of kaolinites, that of illites, which you see in the figure, and these smectites and some combination. Smectites are very thin layers made of 3 stacks with water and ions in between, and they have actually an enormous surface area, if you think. So these are very thin sheet, like like proof pastry, basically, very thin layers with something in between these layers. If you consider that a single gram of monorelonite, which is the most active clay type, has a surface area, an outer surface, which is exposed to the elements, to water, to air, of about 800 grams per 800 square meters per a single gram of monorelonite. Now, interestingly, the surface of this clay is not even electrically neutral, because thanks to isomorphous substitution in the silica layer, typically sometimes silicon is replaced with aluminum. In the octahedral layer, aluminum is typically replaced in some sites with magnesium, with iron, with manganese. You have a net negative electrical charge on this surface. This charge generates an electric field. The amount of charge is actually pretty large. In a monorelonite, it can be up to 100 milliequivalent per 100 grams, so 1 equivalent per kilo in monorelonite. It's pretty large value, which means that the electrical field on the surface is pretty strong. What does this electrical field do? Well, first of all, clays exist in a hydrated form, so they are surrounded by water molecules. Water molecules are, on average, neutral, but they have a separation of charge because of their inner arrangement between hydrogen and oxygen. So there is a partial positive and a partial negative charge, a dipole, and this dipole actually orients itself inside this electric field, and basically the positive part, the hydrogen, is more attracted to the surface of the clay, while the oxygen is repelled away. All these attractions form a certain structure of absorbed water, we call it absorbed water, surrounding this clay. So the so-called diffuse double layer. In these layers, water is more or less tightly bonded to the surface. You have a stern layer where the first molecules of water are really bonded. It's called crystalline water there. It's almost like frozen water in the sense that it behaves like a solid. You cannot remove it. And while you go farther away from the surface, water is more free because it feels the electrical field less. Water, it's never only water, H2O. You always have an electrolyte. Mainly, you have ions dissolved in any water, groundwater, seawater, and the ions also are either attracted, the cations, or repelled from the surface of the clay. Those are the anions. So there is all a sort of interaction around the surface, and this interaction actually causes a variation in properties of this clay. Just to show you, I see that the slide comes with a little bit of delay, but eventually it will get there. The first 4 molecules of water basically are that of those of the stern layer are responsible for a crystalline swelling in clay. So if you start with a dry clay and you provide water, for example, through air moisture, imagine you have clay straight from the oven and you put it in a container where the air is humid. Water will be attracted to the surface of clays. It's a hydrophile, the clay, and it will start to occupy this tightly bonded, to form this tightly bonded layer around the clay particles. One layer, then a second layer, then a third, then a fourth in discrete fashion, up to 4 layers. Then the charges are balanced enough to produce a diffuse layer, and that's what happens when you continue to saturate the clay in this way, because 4 layers of absorbed water is still not saturated clay. The clay is completely unsaturated. Then you have a formation of diffuse double layer up to full saturation, where you basically start to have free water in the pores. This free water in the pores is what is responsible for the permeability of the clay, which you know is typically very low, and that's because most of the water, especially in certain types of clay, is actually absorbed. It fills the surface of the clay. It's close enough to the surface of the clays to be electrically attracted. Only part of the water is free to move in the pores. I find these are publications from Professor Di Maio from my institution in Italy, about 20 years old. On the left, you see sedimentation tests. So what she did is basically she put a spoon of clay, a spoon of dry clay, in a cylinder with about 1 liter of water, and let it mix it to produce a suspension, and then let it settle down over time. And she noticed that depending on whether she had pure water, distilled water, or a concentrated sodium chloride solution, which could represent a condition like seawater. These are marine clays that are formed also in marine environments. So if you take a sodium bentonite in distilled water, which could be representative of condition at the bottom of a very pure high elevation lake, it settles with a high volume. That's because the diffuse double layer are very nicely developed, because there are no ions counterbalancing the charges of water. So the effect of the surface charge of the clay is felt for a long distance, and this double layer can fully develop. If you have a salt solution, there are cations. There is the sodium in the solution, counterbalancing the surface charge, which is negative, of the clays, and so the diffuse double layer are much shorter. The volume is smaller, and not only the volume is smaller because the structure has a lower porosity, because the particles are basically shrunk, because of the smaller diffuse double layer. Not only, actually, the porosity that is left there is free for water to move. And in fact, a bentonite in a salt solution even though it's more compact, has a lower volume, actually has a much higher permeability, 2-3 orders of magnitude higher. The opposite happens in another type of clay, which is the kaolin. Kaolin is a kaolinite-rich clay, where in water the structure is more compact, in salt solution the structure instead is more open with a larger volume. Not only the volumes change, but also the timing of this sedimentation process. If you want to make a suspension of clay settle in the clean water, in distilled water, it's going to take years. This is how long it took to get the first picture in distilled water, 1,000, 2,000 days. So basically several years before you got a clear supernatant above this suspension, because bentonite, non-morillonite particles are really, really tiny and really they don't settle. If you have muddy water with bentonite and you don't have ions, this muddy water will stay muddy for a very long time. It will never clear up. But if you have a salt solution, so the same clay in seawater, or if you add salt to the water, it's going to flocculate and settle within minutes, if maybe 1 hour or 2 maximum. So the sedimentation, because the particles flocculate, in fact, they get bulky, and so they precipitate. Basically, you have a precipitation of the clay. Very, very interesting. But if you move farther from the sedimentation, so it's where the clay is actually formed, to the basic properties, you will also see, now that the slide comes up, that if you do a basic identification test of a clay, liquid limit, let's see just the right part here and not complicate our life with non-polar solution. But if you have a clay and you prepare it for a liquid limit test, which is a standard test in the laboratory, you do it with distilled water, you will obtain very large value of liquid limit. If you prepare the same material with a concentrated salt solution, you will obtain much, much less liquid limit, and hence you will obtain less plasticity index, less activity even the clay. Basically, the salt solution is inactivating the clay. It's making it stronger by inactivating it. So you see the big difference when you go from 0 to even small concentration and then larger concentration. If you then are in a technical laboratory and are testing these clays in water or in salt solution, you can also see what happens in an hydrometer test. Those are really beautiful, especially in morillonites, and you see the left part of the slide, because morillonites, not only after suspension, they are compressed, or after preparation with standard metals, they are compressed, they stay with very large void ratio, very large porosities, and even when you load them and then unload them, they recover that porosity, because the double layer, I say, in general has an elastic response. So you can compress it and then it swells back almost to the initial value after structural rearrangement, but good part of the behavior is recoverable. This does not happen in a salt solution. And think that a pure bentonite might have, at low normal stress, those are typical of Landslide, void ratio of 5, 7, 10, but the same clay in a salt solution has void ratios only of 1, which are basically comparable to those of the kaolin. So you basically, by changing the pore solution, you are changing completely the volumetric aspect and the volumetric behavior of these clays. Not only you can prepare laboratory samples with a salt solution, you can actually expose samples to a salt solution during the experiments. You could make a test in which you start with distilled water and then you expose the sample to a salt solution during the experiment. Or you can do the vice versa, which is more interesting because it's closer to a natural phenomenon. You imagine a clay that is sedimented at the bottom of the sea, and then it's covered with more sediment, so it's loaded. Then, because of tectonics and erosion, is unloaded, and this layer of clay now is part of the slopes of a mountain. It's actually what happens in the Mediterranean. The Apennines in Italy, those are made of marine clays that are now exposed to rainwater. And what happens when you expose this clay to rainwater or distilled water in the laboratory, this clay swells enormously, and become also much softer, much more compressible. This swelling is associated with a weakening, a softening of the material. So you can already think that clays, marine clays exposed to rainwater or to fresh water from aquifers are certainly more prone to slope instability phenomena. They can flow down in earth flows, basically. They can slide because of the weakening. And we see this weakening, of course, not only by the volumetric response, especially we see it in shear tests. Very briefly, you can conduct triaxial tests on samples that are saturated with water or with the salt solution. You will see that for active clays, typically the material in water has half the strength of that in salt solution, saying that when the clay is born at the bottom of the sea is strong. The clay on the slopes that we find now on the slopes and in the landscape is much, much weaker. This can be indeed a problem. You see this in triaxial tests, you see it even better in direct shear tests, in ring shear tests, where you are actually looking for the long-term, large deformation behavior of this clay, which is the typical condition in the shear zone of landslide. Again, an active clay like this one on the left, in a concentrated salt solution in seawater will have a residual friction angle of 15, 20 degrees and even more. The same clay prepared with or exposed to distilled water, or think of rainwater, has a friction angle that is not 20, not 15, not 10, it's only 5 or 4 or even 3 degrees. And that means that a slope made of this clay can have landslides almost on flat land. They can go when the slope is just 5 degrees, 3 degrees only. This is just saturated material. There is no effect of pore water pressure. I mean, even in drained condition, just because of the loss of salt, this material is so weak that can slide in and form indeed very gentle landforms. Now, what are the actual implications of all these for real landslides? I will try to be very quick because we have been studying with the University of Basilicata in Italy a system, I would say, of landslides in a section of the Southern Apennines in my region, which is Basilicata, where you do find indeed many slow-moving landslides. Roberto, can you hear me? Yes, because I think it disappeared for a moment. Okay, you have many slow-moving landslides in slopes that are really gentle, less than 10 degrees. These materials are active clays, and if you see their behavior. Now, I don't have the time to go into the specifics of this landslide. There are normally millions of cubic meters. They are earth flows that move very slowly. They are deep, 20, 30, 40 meters deep in some cases. They move millimeters per year, centimeters per year. They are creeping landslides, so-called. They do respond in a certain way to the external environment, to the rainfall. But what is interesting for me to show is how these clay layers present themselves in terms of pore water composition. We did a number of experiments in which we evaluated the composition of the pore fluid of landslide soils, of the stable formation, of surrounding areas also. And what we found is a profile of the type which is shown here. In the years, actually, we did many of these profiles, not only for this landslide, for other landslides, and also for other landslides in other regions in the Apennines. And all of these experiments confirm one thing. There is a profile showing a transient response, a transient behavior. Something is happening in this formation. These clays are also today losing their salt because they are exposed to rainwater, they are exposed to freshwater aquifers. What is very interesting about this vertical profile of concentration is that you find basically zero concentration at the surface, but then rather quickly you reach very high salt concentration. Now, in these specific locations in the landslide, at depths of 20 to 30 meters, you actually find a composition of pore fluid which is very close to that found in the seawater, basically. And that means that after millions of years, these clay formations, which have emerged millions of years ago, but they are now at the surface because this mountain range is eroding. So basically you have formations that are coming up to the surface, and with all this time, they still preserve the original pore fluid, which is going away now that the pore ions are going away as we speak, let's say, and they form these beautiful profiles. Now, I've already shown you results of shear tests, but I would refer them again to those, specifically to those, to the case of this landslide. And in this material, which is not a monomorite, cyanide, has friction angles in distilled water, which we evaluate in the laboratory of 8 to 9 degrees. But if you use undisturbed samples, or you use the original, the natural pore fluid, you will get 12 to 14 degrees of friction, which actually correspond to the results of back analysis. So if you actually want to do a back analysis in marine clays, you have to use not standard laboratory tests, but laboratory experiments done with preserving not only the clay minerals, but also the pore fluid composition. Interestingly, if you expose this material to more concentrated solution, you will get higher strength, and even much higher if you change sodium with potassium, just because some more things happen within the clay. But basically also here, from behavior in natural condition, 13 degrees of friction, probably original seawater, 15 degrees of friction, distilled water and current surface behavior, 89 degrees. There is possibility, if you want, to replace the pore fluid with something else, potassium instead of sodium, and actually obtain incredible strengthening up to 20 degrees of friction angle, which is actually a suggestion, a way to possibly stabilize this landslide. I would like now to show you briefly also a couple of tests that we also did, where instead of conducting conventional direct or link shear tests, we modified the apparatus to conduct shear creep tests, meaning that we applied conditions more like to those of a real landslide. We applied a constant shear force. Landslides are not moved by a motor that pushes them, no? They are moved by the gravity, which is more or less a constant force, of course, with caveats, but basically a shear creep test is closer to natural conditions. And if you prepare a sample with a concentrated solution, I show you now in the entire snapshot, with a concentrated solution, so that there is no creep displacement because the material is strong and the shear force is small enough, but then you replace the solution with distilled water, causing a weakening, which is the same weakening that it might happen because of exposure to rainwater. You are weakening the material, reducing the safety factor of the system. You are triggering deformation, you are triggering a secondary and a tertiary creep until failure. So you can activate a landslide by making the soil lose ions, lose the seawater being replaced with fresh water. I will skip on some detailed explanation on what happens in this experiment, and also, of course, I am welcoming questions in live or also later. No problem, you can contact me to tell you something, and because I want to reconnect to the presentation by my colleague Marco Locke, who happened before mine, not later, but still I would like to reconnect to that, and moving from the topic of chemistry to that of temperature. The thing is that chemistry chemical reaction, in this case ion diffusion, not chemical reaction, ion diffusion. So the loss of ions in the slopes is actually a very, very slow process. That's because the permeability of these clays is very low, and diffusion coefficient of ion in the slope is also very low, and because the slopes are big anyway. You know, in a laboratory specimen, this diffusion happens within days or weeks. You can imagine, and the specimen is a few centimeters. In the field where you have a slope which is 1 kilometer long and there are formations, and formation is 100 meters deep, well, the things happen on a completely different time scale. So this is a simple exercise of modeling where on the left you see a profile of concentration if you started with the entire slope at seawater concentration, 35 grams liter of ions, and let it be exposed to rainfall, to rainwater from the surface, which triggers some seepage inside the slope. After 1,000 years, you see that you are starting to remove the ions, but basically you find very high concentrations already at 15, 20 meters. So at a depth of 20 meters, you are already pretty close to seawater concentration. At 40 meters, you really have seawater concentration. Now you see the concavity of this profile, and see on the right the profiles that we actually measured in the field. This is not at all a steady state condition. It's a transient, it's an initial transient, meaning that this surface layer has not been exposed to rainwater for long enough. I believe that because with erosion, this is kind of a fresh layer of soil that has been exposed and is being softened and weakened by the action of rainfall. Of course, this is an example, very simple, with homogeneous slope. You could imagine that instead you have discontinuities, you have a softer landslide material over a harder, more consistent formation. You might have a shear zone that might be more permeable also than the formation, which is over consolidated. We prove with modeling that the presence of a landslide actually accelerates the loss of ions, because that softened moving material is losing ions faster, but overall, still this transient is very far from a steady state condition. A steady state condition with a salt source, which is very deep, it's hundreds of meters deep, would mean almost complete depletion of the ions in the first 50 and more meters of the ground. And this steady state condition can be reached in many tens of thousands of years. So the take-home message from this is that the ion composition, the ion concentration in the pore fluid affects the properties of clays, of clay formation incredibly, but the change of properties with time, which is due to the variation in ion concentrations in the pore water, is very slow. It's a very slow process. It's not a process that can explain the activity of a landslide from 1 year to another, unless something big happened. It certainly cannot explain seasonality for as long as the material remains saturated, because if the material desaturates, it's another word. But in the shear zones that are deep, there is no way changes in pore fluid composition are so seasonal or so quick to explain a sudden reactivation of a lens. They can, however, explain very slow, persistent creep displacement, which is what we observe. We observe this because as the material is sliding down over gentle and more gentle slopes towards the river valley, it's actually still losing more ions, still getting weaker, and still continuing to move. Millimeters per year over scales of thousands of years actually can make sense. And the landslide that we are studying are actually landslides that exist for hundreds of years. In fact, now this kind of slow moving, slow erosion of the slopes. But now to reconnect to the topic, I want really to make a little change of topic in the last minute, to the topic of my colleague Mark Colloque. There are other things that can explain seasonality in landslides in gentle clay slopes. And one of these things is, of course, rainfall, the patterns of pore water pressure, but that's not enough, because even temperature can be responsible for a seasonality in behaviors. My colleague Locke and I did an experiment in data-driven modeling where we took the clay slopes in the Apennines, the gentle clay slopes in the Apennines, and we made a susceptibility mapping using a small number of covariates, including temperature, to see whether actually temperature could explain the activity of these clay slopes. And we were very, very surprised when we found that in our susceptibility maps, the land surface temperature of these slopes was actually a good predictor of instability. So we found that warmer slopes were weaker, and we demonstrated this in the laboratory, like Marcus showed you, were weaker and so consistent with more activity, more landslides in certain areas of Italy, of my region. This is Basilicata. One of these landslides is actually the landslide that I showed you before. Also, this is consistent now with a pattern of warmer slopes, weaker, meaning weaker slopes. Now, if you think about this together, now the two topics, chemistry and temperature, seem completely disconnected. But in reality, the fact that higher temperatures correspond to lower strength in other seas as well, higher compressibility, also, is actually very consistent with chemical processes, chemical reaction, and chemical processes that happen within the clay in the microstructure. Think of thermal expansion, so it's physics. Think of thermodynamic reaction. Think of the shift of a chemical equilibrium reaction between two parameters, but two states according to temperature. When temperature increases, water swells, minerals swell, water gets more fluid, the bonds are stretched, the double layers expand, the material softens, and so the strength also can decrease. I would like to probably, without even showing the last slide, I would like to conclude this presentation with this, Roberto, and I wonder whether there are any questions from the audience. And thank you very much for your attention, of course.
Thank you so much. I remind all those following us via YouTube, feel free to write your questions in the live chat.
Of course.
And for now, I don't see any questions. Thank you so much for your excellent presentation. Thank you for your very good disposition.
Thank you, Roberto. I think I forgot to add my email on the slide. So, but if anyone wants to ask me a question later, you can just look up my name in the internet. You will find my socials. You will find the web page of the university where my email is there. So feel free to contact me. I'm really happy to provide more explanations, of course.
Thank you so much. So we are back, and I am very happy and honored to introduce our next speaker, Dr. Olivier D. White. Thank you so much for accepting this invitation. Thank you for being part of the Landslide Scientific Assessment Conference. It is your time, but please, as I ask other speakers, can you introduce yourself and tell us whatever you want about your research, and you can start with your presentation. Thank you so much.
Okay. So thank you very much. So a very quick word about who I am. So I'm a researcher based in an institution which is called the Africa Museum in Belgium. So it's a research and a museum together, and we have a mission which is doing long-term in research and partnership with Central Africa. And one of the key topics is natural hazard and risk assessment in this part of the world. And my research and what I'm presenting here is in that framework. And what I present now, I mean, it's a photo I took about 10 years ago. And so you are all landslide experts, and you see that you have different landslides, recent landslides on these photos, and shallow landslides, deep-seated landslides. You also see that the entire landscape has been deforested. So we are in a tropical region, which normally is covered by forest. And you see that everything is now cultivated. And besides that, you have a nice river that is at the border between two countries. And close to the river, you have steeper slopes. So the river has incised the mountain range very quickly and very recently. So you have a sharp distinction between a regimented landscape and a relic older landscape. And so you're in this region, and then you just move 20 kilometers to the north, and you have a completely different landscape. So it's the same lithology, it's the same climate, but here you are in the city of Bukavu. So you are in the DRC. And if you look a little bit at the morphology, you see in the background, you see a scarp of about 100 meters, which is the head of a slow-moving landslide. So the type of landslide that were mentioned in the former talk. And this slow-moving landslide is a few thousand years old. It's been there for from purely natural origin. And now you have 80,000 inhabitants that live on this active landslide. And with these two photos, I just want to highlight key challenges that we have in landslide research community, especially in tropical environment in Africa. So basically, you have a lot of different processes like everywhere, but you have land use, land cover changes, you have urbanization, you have urban growth, and you have also population exposure. And these are topics that are clearly well in line with very recent assessments about urban sprawling, climate change, and growing exposures across the world. So this is with these two photos that I am here to present you some insights that we have for tropical Africa, and more specifically the western branch of the East African Rift of natural and human-induced landslides in changing environmental conditions. And the work I'm presenting here is on behalf of many other people that I've been working with over the past 10 years. So tropics means land use, land cover changes, means urban growth, for example. But if you look at this photo, this visual from the last IPCC report, what you clearly see is that you have problem of data scarcity. Here in terms of climate knowledge, but overall you can apply it for any kind of topic, which is just even like population counts on the knowledge about the lithology. And in this case of the IPCC, for example, in the region of Central Africa, they can not even assess trends in climate, for example. So this is a very key important to recognize when you work in this environment, but also in many other environments like in Latin America, of course. And then now I zoom in into the western branch of the East African Rift, here with three figures. The central one, I think that everyone knows, that global susceptibility assessment made by the colleagues from NASA a couple of years ago. And the lightest the colors, the most susceptible the landslide area are, the area are to landslide occurrences. And so if you look purely at the susceptibility level, Africa has some hotspots. In terms of landslide, this is less pronounced than the Andes, for example, the European Alps, but still this is something quite important. Now, if you look at this susceptibility context and you put it with the population context, population density, population vulnerability, and potential of population growth, you are in one of the most exposed places in the world, and the situation is expected to worsen as the population is going to grow in a very important manner in the coming decades. So that's the context of our research. I mean, societal needs, data scarcity, and of course, diverse processes. So the results I'm going to present are framed around pluridisciplinarity and holistic approach. So it's framed around strong partnership with African institutions. So depending on the partners, we have different research expectations, different research needs, focus on specific landslides, focus on regional level, focus on the geological context of the landslides, and many other questions. So we do work with satellite remote sensing, which is optical or SAR imageries. Radar, very important. It's one of the regions which is the most covered by clouds through the year. So radar is very an added value here. Of course, field work, data acquisition, basic climate data, and rain gauge networks. Citizen science is also something that we work with, and developing research strategies in data scarce context. So quite often, established method, for example, in Italy, would not necessarily work here due to different types of data context. And then, as I said, I am in an institution which is also a museum, and for that we have archives. We host copies of, for example, hundreds of thousands of historical archival photographs. So these photographs, they are very good to track back the land use land cover changes over the past decades. So now a first inventory over this region. You have about the size of the region, so it's about 400 kilometers long from north-south, 100 kilometers wide in terms of longitude. And the first thing is, of course, to identify the landslides. And it's an ongoing work, and so far we have been mapping about 30,000 landslides in that region from satellite images, but also from field validation. And one first thing that you try to do when you have so many information is to look at the trends. And one of the key aspects to look at the trends is to look at the susceptibility patterns. And here, this is a regional susceptibility model that has been developed. I'm not going into the details, but we have also an update lithological information in that specific context. And that's a model that clearly outperforms continental and global scale models here. A tool which is still useful for looking at regional trends, of course. Now, if you look at this tool for site-specific investigation, of course, it has no value mostly. Then still at the regional level, let's have a look at the types of landslides that we have. And here, this is a very common observation, is that every season brings intense rainfall, and quite often you have these clusters of landslides. Some of them, they can be grouping like several thousands of landslides that would occur just sometimes in just a couple of hours. Just an example here of these debris avalanches in Rwanda. And that what we see is that those events are clearly rainfall triggered, but for any kind of recent landslides that we have observed over the past decades, we have nothing which has been associated with seismicity, for example. Although we are in a rift context, and in a rift context, you have active faults and you have also active volcanoes, for example. So nothing could be related with that. Not saying that seismicity is not a trigger of landslide, but over a period of a few decades, this is simply not observed here. So now looking at these landslides and these rainfall triggered landslides, we clearly see a nice seasonality pattern. So on this diagram, you have two informations. First, you have the monthly rainfall, and you see that you have two peaks of rainfall. So these are the blue bars. And next to that, you have the black curves, which is the number of landslide events that have been accurately dated in the region. So a few hundred dated landslide information. And then you clearly see that the peak of landsliding is arriving at the end of the second peak of rainfall. So clearly, it shows the role of antecedent condition. You have the triggering rainfall, but you have, of course, the role of antecedent condition, which is important here. I'm not showing those results, but this clearly helps into designing rainfall thresholding approach in the region and, for example, lead towards early warning system based on this antecedent context. So when we have shallow landslides, we clearly have also in mind the role of human activities on their occurrences. And one of the key aspects in terms of human activities in the region is deforestation. So we are in a place where population has been multiplied by 10 to 12 over the past 60 years. And so it means lots of land encroachment and lots of deforestation in some places. So we have had a look at the past 20 years in terms of landslide occurrence, and simply on Google Earth looking at the sequences of the images. And based on thousands of landslides, we could then analyze how much years after deforestation landslide can happen. And then we have looked also at the landscape rejuvenation. So remember one of my first figure, I did show you the presence of a river system that deeply incised the landscape. So here we are in a rift context, and clearly you have active faults, and within the rift, you clearly have a steeper and more recent topography. So that's a bit like maybe in the European Alps, they have been eroded recently by glaciers over in the past 10,000 years. So this has an effect. And here you clearly see that you have a neck point, which represents this rejuvenation. Downslope the neck point, you have steeper, younger slopes. And here you have also the presence of a landslide. So we have had a look at all of these. And what we show is that deforestation increases landslide activity for a period of about 15 years. After, you are back to a normal situation. And we also show that deforestation overall increases landslides more into the regenerated landscape. Again, it's kind of a complex relationship between slope, between seismic background, between weakening, between weathering. I'm not into the details here, but just it's very important. Just we show the impact of human activities, but the impact of human activities changes according to the, let's say, geodynamic context of the mountain range. So you have in mind this impact of deforestation that will last about 10 to 15 years. We have also the regional model about the susceptibility assessment, and you have this landslide that have been observed over decades. So basically, we can link the occurrence of landsliding with the pattern of deforestation. And we have historical photographs, so we were able to reconstruct the forest pattern from the 50s there. And then through several modeling steps, we're creating the annual change of forest cover. And each time there is a pixel that is deforested, it changes the potential of landslide for the next 15 years. So combining all those, plus changes of population exposure and vulnerability, we were able to actually show that between the different countries that are in this region, the risk has evolved in different manner. And this is summarized in this conceptual figure, which applies mostly for Congo. So there, over the past 60 years, you have an increase of population. You have this population, which is also migrating towards the naturally more pronounced zones in terms of landslides, simply because of forest and deforestation opportunities, but also because of mining activities. And mining activities leads also to road construction, which leads to more landslide, but also the mining site, you have more landslide that can occur. So this is quite a complex thing. And we show that, for example, in the other countries of Burundi and Rwanda, this impact is less pronounced because of different governance context. So looking at the landslides, we have looked at the shallow landslides, but we have looked also at the deep-seated landslides. So here are examples of new landslides that have occurred over the past decades, from a photo in the C50s where you have nothing and the situation in the current conditions. And we have looked also at the amount of landslides, the volumes, and then we have looked at the mobilization rates of landsliding. So basically, how much material do we have from landslides that have been mobilized over 70 years? And in this figure, you have two main bars, rejuvenated and relic landscape. And on the y-axis, you have the landslide mobilization rate per square kilometer per year. And you clearly see that overall, we have more landslides that are mobilized within the rift than outside the rift. And you see that in blue, the main contribution comes from deep-seated landslides. They are much less than shallow landslides, but overall, their volume is much bigger. So in the former slide, I did show you the risk about shallow landslides and the importance of a lot of problems associated with these shallow landslides. But when you look then at the geomorphic impact, this must be nuanced because, of course, then geomorphic impact is more associated with larger events. And then we've looked, the darkest colors are showing the anthropogenic context. And then you see that overall, the human influence is rather limited in terms of mobilization rate. Once again, a lot of impact in terms of occurrence of shallow landslides, but overall in terms of sediment budget, for example, at this regional scale, not much. I want also to stress something that we have faced in looking at this human and influence landslides, is that the current classification of landslide processes miss the inclusion of the Anthropocene context. So here, importantly, this is to look at shallow and deep-seated landslides, but also road landslides and mining landslides. This is more technical comment here, but this is really something that we have seen and that we try to adjust in our research in the region. So there were examples at the regional scale. Now I want to move a little bit some examples, site-specific. And we have been discussing about, let's say, deep-seated slow-moving landslides in the former presentations. Here, this is an example of a landslide which has been well monitored with hundreds of satellite images from radar and optical images. And we could really track by the origin of the landslide, this development, and we could show that the landslide is responding very well to the rainfall seasonality. It's clearly a seasonal pattern, and much less, and even no, to the original seismic activity. And that's a purely laboratory landslide in the region. And then we have other deep-seated landslides. And if you remember, you have this first photo of Bukavu, which is also a deep-seated slow-moving landslide. And that we studied, and this landslide, although it's in urban context and although it's much more older, is behaving exactly the same with this rainfall seasonality into the dynamic. But then we've looked at this landslide behavior and we've looked at the past. This was the situation in the 50s. So you would see that there is almost nothing which is built on this landslide. And then we could demonstrate that over the past 60 years, some parts of the landslides have accelerated, although having this seasonal pattern, due to water concentration, runoff concentration due to urbanization. So here, that's a site-specific investigation where we clearly demonstrate the role of urbanization on the acceleration of slow-moving landslides. And Bukavu in itself, for example, I give you here some overview photos of the city. It's just like 30% of the city is built on landslides. You have the slow-moving landslides, but you have also terraced hill slopes with new houses, and it has also an impact, road cuts and everything. So just to show you the importance of this urban environment in landslide context. So Bukavu is a case of a city where everything is built on the landslides. If you go a bit more to the south, you have the city of Bujumbura in Burundi, and that's a bit different. You see here that the main city is in a plain, and then I would say the very, let's say, more developed or wealthier areas are developing onto the hill slopes. And we have mapped here, so basically this shows the entire hill slopes that are just behind the city. So the city is here where I show my cursor. You have thousands of landslides there, and I want to show you, not in detail everything, of course, but two elements about human influences. First, in the city, or connected to the city, we have very large gullies. And these gullies have been associated with urban sprawling. And they are so large that they trigger new landslides, sometimes kilometer-scale landslides. So you have clearly a landslide problem here, which is associated with, as a trigger, erosion processes. Then I want to stress another element, and this is an example of an extreme rainfall event that has occurred a couple of years ago. It triggers hundreds of landslides, but also it triggers flash floods. But then as you are close to an urban environment, you have a lot of human disturbances, and you have quarrying and mining activities in the river or outside the river. So this has played a role, and you clearly have mining sites that have delivered a huge amount of sediment to the river system, blocking the river, creating temporary dams that, when bridging, has increased and exacerbated the impact of the ongoing flash flood events. So that's clearly a nice example, I think, of compound cascading event in this context of urban influences. Then I'm progressively moving to the end of my presentation. And here, this is a landscape that you see, typically mountain landscape in the rural environment. So I'm leaving now from the cities. If you look a little bit, you have different features that you can observe. You clearly have different, the red arrows indicate landslide heads. You have a lot of large landslides. And you see that they're associated with a fault scarp here. So you're on the rift context, and you clearly have this large landslide that have a seismotectonic origin. They are 10 or 1,000 years old at least. So they are natural main feature in the landscape. They are there in a natural way. And you see that people have to live with that. They are simply having no choice but using them. And so we have asked those people if that was a constraint or not to live on landslides. And there were nice answers in a way. And then for many of them, landslides were an opportunity. I mean, not all of them, of course, but the large and old landslides, they, as depicted here, they have, let's say, flatter patterns that allow different types of land uses. You have also wetter soils that allow different cropping. The main scarp is also sometimes an opportunity for raw material or even acquiring or mining activities. So this is also something to consider. I mean, that it's just above all a natural process. And in some cases, the rural communities, they know how to face with these natural processes. So I wanted to finish with this kind of positive view. I like to highlight here the contribution of the PhD students that have been working on this. And then as a concluding slide, I'd like to show you the perspectives about this work, and I thank you.
Thank you so much, Dr. Olivier. It's wonderful to learn all about your research, what you shared with us today. I also remind all our attendees, feel free to write questions in the live chat. Yeah, I'm taking a look right now at the chat. Okay, I don't see any questions here. So thank you so much, Dr. Olivier. It was my honor that you attended this event and to be part of this.
You're welcome. You're welcome.
Thank you. And we are back. I am pleased to welcome Dr. Lorenzo Orselli. Thank you so much for accepting our direct invitation to be part of the Landslide Scientific Assessment Conference. It is my honor to greet you. How are you, Dr. Lorenzo?
Many thanks, Roberto, for your invitation, and I share this presentation as well. You can download it in RazorGate. Or we have the link active, and you can download it. Here, for future questions, you have my email and also my personal webpage. Well, the presentation is related to SSAP 6.0. That is a full freeware software for slope stability analysis. I made only a short, very short synthetic introduction on SSAP and objective tools and something like that, and some very few application of it in Mexico and Italy, even if it has been used much more in our we have a small abstract. Well, slope instability is a deep interaction phenomena between geology, geomorphology, geotechnics, in some cases also in volcanology. This was one well-known case of in Salvador, Las Colinas landslide that produced a lot of victims some years ago. But the slope stability analysis is only matter of geotechnics. Is not, because we have a lot of interaction that is well known, and this is mainly important for other assessment. And we have a matter extremely complex on it. For example, this well-known case of an image of Civita de Bagnoregio, Italy. This is a very area with strong dynamics of landslides, where the geotechnical marine sandy clay deposits interact strongly with volcanoclastic and volcanic deposits. This is an image of Nicola Casalli, and this is an area that is studied from long times ago, but extremely important, for example, for to the interaction that I indicated. So these kinds of interaction are fundamental for definition of geotechnical hydraulic model of a slope in coherence with the stratigraphic model, treatment parametric uncertainty and scenario analysis, and of course the kind of use of computational model used to evaluate the degree of stability for different purposes. The slope stability and its verification is extremely complex because we have interaction of the old kind of components. Some of components are related to geometry, stratigraphy, until hydrogeology, geomechanics, and other are the kind of model you use of it. For the reason, our objective, our purpose is the evaluate assessment hazard of slope stability. So we have some possible questions to be answered. For example, how to manage this kind of complexity, the possibility of can analyze different kinds of are possible reliable method for evaluate safety factor or degree of rating of stability. How kinds of software tools are reliable, and exist some of type of software at zero cost. One possible answer is the SSAP software that available at this site. Of course, is no profit purpose software, but only for research and professional application, and also for the didactical purpose, that have is website in English and in Italian and Spanish. So we can go there to make to found much more information, more detailed information. The license is you can download the license, where you are completely free to use it for individuals, students, geologists, engineers, and public administration everywhere. No, it haven't any kind of profit aims. This is important. The story of the development of this software is very large, but just to summarize, in the last was special credits to CNR in Italy, and then CONACYT Mexico for different projects and funds that as a basic for their development during the larger story of the SSAP. Of course, you can evaluate it in the SSAP. This is the last manual, reference manual, that in process of the full translation in English for the 6.0 version. And the goals is to provide the user for ability, the possibility on tools to use advanced limit equilibrium method and other more innovative algorithms and developed by the author, and with the contribution also the people that the user, and during the story of the so you have a lot of time that use web of development. Exists some hybrid methodology technology. This original in where we combine the classical limit equilibrium method with the finite element method. We call this one. This is one of these practically importance. The SAP don't use simplified method, limit equilibrium method, but only rigorous method. And one of the most important things that SAP don't generate exclusively circular shaped surface, are not considered in any case, but can be generated because we use several engine generation and surface generation and search engine that is developed. Some are well known, but others are completely new, and it's used as tools, basic tools, especially when we have so we have a list, but not complete list of classical tools present in SSAP, but also the new components here. So you can look at this website to find most details. We have some graphical output possible, and that get many tools able to evaluate also where can be generated progressive failure in case or excess of pore pressure as well. We have a user interface, English and Italian. You can easily change on it by click a button, and to manipulate the software, and also to generate the data structure as well. We have a list of papers where SAP was used in the past, and with very various kinds of example of application, from volcanoes, planetology, application of stone wall, dry stone wall, of application of various kinds of project and engineering application, civil engineering application. So we have a bit of time for some example application in Mexico, only few. The first time, historically, application in Mexico was the application to the Colima Volcán de Fuego in Mexico. You have here a paper with Lucia Capra from UNAM, Damiano Sarocchi, and Servando de la Cruz Reina. You can download it, and you have a paper with a lot of things inside, so you invite to look for it and search for the application. This was evaluated to evaluate used SAP to evaluate what's the areas of most probably unstable area of the volcano, using several techniques, not only limit equilibrium method, but other methods together. And some improvement of the results was obtained also using successive version of SSAP, where after, for example, the collapse of the dome in the 2015, and using the comparison of volume deficit map obtained with the volcanofit tools. This is a successive analysis, because when this kind of map was available in the 2016. This instead is another different context, the case of San Javier gold mine, San Luis Potosí, Mexico. We have contact in limestone and porphyry gold deposits. The mine chased its activity in 2016. This is the model where the analysis concentrates especially in this area, because it is a urbanized area. And then we have the results of this is a tunnel that enter a old tunnel that is excavated partly by the open pit. And this is the safety map obtained by quasi-FEM algorithms. One of the algorithms applied together advanced limit equilibrium methods. And this is the same, but obtained by when the system of fracture is considered with the pattern of the structural control surfaces in the limestone area. Another case application is instability phenomenon in rural area of Mexico, in Huasteca Potosina, where no authorized excavation earthwork was performed in very steep slope in Pesmayo area, Tamazunchale, San Luis Potosí. This bring to instability, producing in different times cracks and a progressive deformation of this. You have two situation of two moments when a progressive deformation of the slope, a very steep slope. And this is the first topography produced and stratigraphy evaluated in with the geoelectrics SEV and also field survey. And that is the results of the back analysis obtained with all the kind of data using the SSAP application in 2019. This is another application in Mexico, the last one. Master student, past master student, Felipe Baldassar Martinez, in area studied before from many research because of a big flow slide that produced a lot of victims in an urbanized area, because the collapse, after the collapse of the earth deposits of public cemetery. This is not urbanized area, but practically the same because it's a big cemetery of the county. So this produced a big landslide because deposits of the materials on Thixotropy andosol, a cemeterial field that collapsed after a rainfall about of 700 millimeters in 3 days of accumulated rainfall. And is the simulated safety factor after the full saturation. But this also, the results, this kind of output was used also by Titan DOSD to the run-out simulated after, to simulate all these kinds of flow slides. I remember that the number of victims in this case was about 140 peoples. Some example application in Italy. One of the most interesting is this paper with Agnese Innocenti, Veronica Pazzi, and me and others, and Max Ventini as well, Luca Lombardi, Gilli, and Fanti from University of Florence, where this kind of is a collapse of civil engineering pile pier structure collapsed completely in a landslide area. So we made a multi-layer back analysis method that is described in the paper, and the application of SSAP. In this case, a full tie rod and piles was used to evaluate the results. Another important was a recent paper about the instability of Sciara del Fuoco or the Stromboli volcano, these active volcanoes in the center of Tyrrhenian Sea, that in 2002 produced tsunamis because 20 millions of cubic meters of materials collapsed here. a set of landslide produced as also a submarine landslide. This is the various phases of landsliding. This is the different, including submarine landslide, sea level here. And in this paper, we applied a combined failure criteria of generalized Hawken-Brown criteria and Barton-Bandis criteria in Barton, where depending of the geometry and the kinds of deposit, we have combination in rock field volcanoclastic, lava breccia, and lava deposits that partly well known from geomechanical point of view, but not modeled until this moment in way to produce a complete tsunamigenic reconstruction as we obtained it in this paper to different kinds of landslides that can be observed by local FS and EOSR maps. Another similar, but in this case combined with insert, differential insert, was monitoring and modeling moraine landslides. This is a recent paper where we have is a very seismic area in the 1976 was occurred a big earthquake and remobilize this big landslide. But now the processes is the moraine deposits is slow moving area. We have in the paper we have several parameters detected, but one of the most important is the analysis made in this urbanized area in the village with the GPS and insert differential insert. In practical case, also with effect of we have several color map with overstress ratios that is practically related to the inverse safety factor, but indicate the area must with high mobility, and it's demonstrated with the combination of the insert displacement direction. So this is a case of combined output insert detection. So I invite to read the paper and to find some to make your observation in details. The last application is very recent paper as well, new for another times in Stromboli volcano, because they to evaluate with different kinds of monitoring. I remember that one of the most monitored volcanoes in the world, Stromboli, and this is the crater rim and crater terraces that is completely in continuous evolution as well. This area where we are producing lava flow, volcanoclastic, pyroclastic flow, and so on like that. We use another times the same approach with the parameters and combined use of multiple sliding failure criteria, but in this case we in two different dates we evaluated the deformation rate made by GB INSAR in the crater rim, and the details. In this case, the direction is in this section. In this section, as well, we have a very detailed, continuously digital terrain model, because of course here we have not vegetation, but is made by various tools that the researchers use to monitor this area. And the final results with SSAP. The safety factor, of course, in this red and pink and red areas, we have the highest rate of deformation, and that correspond is the crater rim morphology change, because we have two different dates, and combined with the displacement evaluated. I conclude here my presentation. This is just you have my channel in YouTube, where you can find several videos on SSAP. Some of them are in Italian, some are in Spanish, and in English. Some of them are in three languages. So you can choose and you can find also application with in application for some kinds of civil engineering structure for containment and reinforcement. Here you can find my email and my webpage for more information about my research activity. Many thanks.
Thank you so much, Dr. Lorenzo. I am amazed with SSAP 6.0. Congratulations on your research and the development of the software and all the work during all this year. And I am very glad that you presented today at the Landslide Scientific Assessment Conference. Thank you so much.
Thank you, but well, many thanks for the invitation, and many thanks again.
Okay. All right, we are back, and I am very glad. I am honored to greet to meet Dr. Benedetta Dini. Thank you so much for accepting our direct invitation to present at the Landslide Scientific Assessment Conference. How are you?
I'm okay, thank you very much. Thank you for this invitation.
That's great, thank you. So it is all your time. I will ask you, as I have requested the other speakers, please introduce yourself. Let us know a little bit, very briefly, about your research, and now you can continue with your presentation. Thank you.
That's great. Thank you very much. Yes, so I am currently an assistant professor of environmental sciences at the University of Birmingham. I've previously worked in several different institutions, as many of us, and I'm going to present some of the work that I have done largely at ISTER in Grenoble in France in collaboration with CNES, which is a French space agency, but also in my contextualization, you will see easily done with collaborators at ETH in Zurich. So my presentation is going to focus on results that we synthetic aperture radar differential interferometry, and specifically on landslides identification, but landslides precursors. And I will the second half of the presentation on the case study of a landslide in Peru. So I just want to give a little bit of context so that are not overly familiar with INSAR. I have a feel for what we can actually do and landslides. And it's not meant to be autoreferential, but I will use largely my work to give you this context. So currently try to identify previously unknown landslides over large areas. And we can do that in a very simple way by using single interference, which are just a snapshot of the deformation between two SAR acquisitions. And this is just an example. As I show here, we have the ferrometric signal, which is the wrapped phase, that can show some patterns that correspond to activity features. For example, in this case, on a deep-seated landslide in Bhutan. And this can be very useful. We've seen in previous presentations how discovering the distributions over a large area can be very important. It can give inventories to work with, evaluate predisposing factors over large regions, and we can have a first assessment for land use management. And so here of a map that I have compiled with my colleagues for Bhutan, which was a region for which very little was known in terms of landslide area. Only a few cases had been studied previously in this region. And this shows how we can combine different sensors and a large number of produce essentially what I've called a likelihood of activity map, which can be used as a hazard index map. So it shows in relative terms where we have more likelihood of activity on slopes. But the quantification of is actually something that has become increasingly popular, and this is done by generating time series using multi-temporal approaches. Briefly, some examples this afternoon, and they are very useful, of course, because we can get absolute measures, the displacement and the displacement rates. And so we can also hope to identify the actual processes occurring on slopes, even attempt to be a bit more specific about the hazard level of specific sites for example, site suitability. And this is an example of a map that I've produced for the same area that you've seen before using time series, the velocity maps and the cumulative displacement maps. And you can see that there is a lot of information here, but if we compare it with the previous map, we can see that although some of these polygons are in similar areas, there isn't a perfect overlap. Hopefully you can see that. The two different methods that are based on INSAR give different type of information, and they should be looked together as opposed to taken as interchangeable, because they aren't. We can, as I said, we can have a look at potentially site. Even when we process at the large scale, there is some potential in there. And this is just one example of a particular slope that I have identified in this large area in Bhutan, where I did an entire frame processing. And for sure, we can see some slope. They are at most a couple, like 200 millimeters per year. In fact, this is displacement rates. So, sorry, yes. So basically, we can definitely identify some trends, but we have some verification, some validation on the ground, if they look realistic and they're real, or if they look realistic, but they are, for example, underestimated. So here I have a slide just to suggest that there might be a potential pitfall here. So it is great what we can do about what we're looking at. We know that landslides undergo transitions. They can creep really slowly periods of time and then suddenly transition into faster, into accelerations. But also at some point, they can even be governed by different mechanisms and responding to different forcing factors. And they start to respond with phases of acceleration and decelerations, which can happen over relatively shorter period of time. And we capture these with INSAR. This is the question. When I see time series from INSAR, I always ask myself whether we are looking at displacement rates or something that looks real, but maybe is underestimated. So I got inspiration a few years ago from this article from Intreria and his colleagues, and they have shown for this particular landslide in China, which you can picture on the left corner, that they actually were able to retrieve a very nice acceleration signal over the course. And that they've also said that by plotting the inverse of the velocity in this particular case, they were able to retrospect, potentially predict with quite good accuracy the time of failure for these landslides, which would be fantastic if we could do that. But the reality is that the retrieval of reliable time series, so not only realistic looking, but reliable, actually be hindered and is often hindered by low coherence, which is basically an instability of the phase signal, which is given to land cover changes given by vegetation or snow, or even a veneer of loose material on slopes that move like not as a coherent body, let's say, with the rest of with the landslide body. And also because go these phases of accelerations and decelerations, this is also something that complicates the retrieval of this time series. And I just want to show you what I mean. So we have here on the top left a snapshot of the European Ground Motion Service, which basically is an excellent product where INSAR is updated, I think, every 6 months from 2016. So this is incredible what they have. But when we zoom in, so of course, a lot of important information is contained here. But when we zoom in into the two little squares here in France, these are just two. There are many more. We can see that we have very little points, and the few points we have are green, which would suggest that no displacement over these slopes in that period of time. So 2016 to recent, I don't remember when I took this, not very long ago. But actually, there are two landslides that moved, that underwent significant accelerations, so we can't see them with the most classic processing approaches for time series generation. It moved by several meters. Here we have June 2016, July 2016, so well included in these data. And here we have another landslide, which we can see moved by several meters again in the same observation window. Were observed with different methods, so optical image correlation and ground-based INSAR. So we really have to be careful about that. And now we example, which is the Achoma landslide, which is a landslide in Peru that failed catastrophically in 2020, 4 years ago, and it was completely unforeseen. So the reports we got is that locals only started to notice sign of the deformation before the failure occurred. So when there was no time to really do anything meaningful about it. And this landslide was very big, well, is very big. It blocked the river, and it's estimated to be about 20 million cubic meters. So it's, and when we look at another platform that this time is based on work of some of my colleagues in France, this again shows the map based on another approach that is quite common, the ESPAS approach. And again, we can see a big red block, which is deformation associated with a volcano in the area. But when we zoom in into this square, the white square, hopefully you can see it, we can see we have some faint black polygons that are the landslides in this area. And this is our landslide, the Achoma landslide. The insert signal, again, we don't see anything, yet we are well within the window here. So this data is from 2022 and the landslide fell in 2020, but we cannot capture it. So if I show you of the wrapped interferogram, so this raw interferometric signal for this landslide, this is what we see. So even insert, hopefully you can see with your eyes that we have some patterns in the center of this square, which are squares, which are centered over the landslide. You can see it here, and you can see it very well here, but also, hopefully you can see how noisy interferograms are. Therefore, in the absence of a smooth gradient, the retrieval of time series is really difficult. What can we look at instead? So this is a marker and potentially a precursor in space obtained with the coherence. The interferometric coherence, as I mentioned before, is a measure of the phase stability in space, in a window of pixels. And in line with the rainfall, you can see the wet seasons. And we can see when I show you these squares with coherence maps, shows some very interesting rope-like features that appear to mark what will become the band slide. And the interesting thing is that already from 2015, even if I don't show it on this slide, we see it at in time. So that means that this particular part of the signal can, at least in some cases for certain types, can already identify gravitational features well below they are visible on the ground. And when we mean parameter, the coherence in time, here I show the mean, the average coherence within the landslide polygon, which is the area with a yellow line on this graph, and the average coherence in the surrounding area with the green line. We can see that it goes up and down following a certain seasonality, and it goes down when during the wet season, as we can. And if we look at the very end of this temporal window, in a few months before failure by the red line, we can see that there is a big departure of these two curves. When we compute their ratio, landslide, over the coherence in the surrounding area, we see that from April to June, we have a drop in this ratio. So at this stage, I don't know yet how this can be used in a predictive way. We have a precursor that deserves to be investigated further. And this map shows so the image, the data, the cumulative displacements obtained with optical image correlation that was processed by my colleague at ISTER. And we selected a point here where you can see right in the middle of the landslide, more or less, where the displacements were really large. We compared the displacement obtained with the optical image correlation that you can see here in green with my ratio. And we can see that there is a very good correspondence in time when these two signals begin to appear and begin to clear. And then we did another thing. So I will not go into the details of how of the method, but we devised a very a simple method in a conceptual sense to try to extract a dimensionless activity quantity directly from the wrapped phase. So without going into all the processing steps that are required for the classic time series generation. Every point on this graph is an interferogram. that was available to us. And the color difference in the length, so the interval between one and the first and the second acquisition. And we tracked a measure that is a relative measure, as I say, is a dimensionless quantity, in fact. So when this quantity is 0, it means that we don't see any displacement within that. And then above 0, we see some displacements. And here we can see a few interesting things. First, you can see a bunch of interferograms here that are gray. So at this point, the displacement were being too fast. The noise is really too high. No method can allow us to really extract this dimensionless quantity. But we can see that very clear acceleration phases a couple of years before, like within the 2 years prior to failure. And this is also quite nice. They appear to correspond to the onset of the rainfall, which are the blue curves. So every blue curve is one hydrological, so it's one wet season, basically. And we can see that there seems to be a correspondence there, but in the season, in the dry season between 2018 and 2019, despite the rain stopped, there appears a continuation of the activity of the landslide. Then the landslide quietened down again in 2019 into 2020 to resume again in 2020. And interestingly, the runaway acceleration was not in a period characterized by higher. So this seems to point to some sort of progressive failure. So there is a certain control of the rainfall, but there is some going within the landslide itself that is explaining the displacements. We can also see that we have, towards the beginning of our test, we have 5 interferograms that appear to show some displacement that occurred over a very short period of time, and then the landslide stopped. When we look at, for example, seismic activity, so the green bars, on this graph represent the peak ground acceleration earthquakes in the proximity of the landslide. We can see that probably some of these events, these displacement events, were triggered by higher PGAs. In fact, we don't see as high PGAs later towards the first part of the period. Here you can see potentially, I told you, I extracted a dimensionless activity quantity, but then here we have cumulative displacement in millimeters. So I basically just use ways to estimate what could be the displacement. This is not really accurate, but it gives a sense of what the displacement on the basis of the gradients that I was observing in the INSAR signal, but I don't have time to go into this detail now. But it's just an estimate, so it's not meant to be a correct measurement. But yeah, so what I think we're seeing is probably a period in which it's really undergoing these transitions, this fast transition between accelerations and decelerations. And when we plot the inverse velocity of these 3, for example, we can see this asymptotic decay, which would really exactly show that we are probably in this sort of phase if we're looking at the creep history of the landslide. So this is very interesting because basically we are revealing all of this in the absence of a classic series generation. The other thing the last thing I would like to show you is the complementarity that there is between the optical image correlation, which is in blue, where we can't really say a lot in the period between 2018 to 2020, but the last acceleration is picked up really well. And INSAR, which is the method that I have devised with this study, where we can actually see accelerations in the years prior to failure. So this would give a very long period of time to start to investigate better what we're doing on this landslide. So just to conclude, we are now, I feel like I have still this question whether we need specific tools for landslides when we're using INSAR, as opposed to relying on the most classic approaches. Monitor more reliably landslides from space. So I just conclude leaving you some of the key messages with the methods that I've shown you. well, what I haven't shown you, but I've shown you the results of those. We can, as a precursor, up to 5 years before failure in this particular case. And I haven't shown this, but I can tell you that this was not an within the valley in which this landslide is located. And also we can show that despite the noise, which would have hindered the generation of a classic time series, the rapid phase signal, which is really the raw interferometric signal, can still retrieve some sort of accelerations, indicating progressive failure, probably, and also showing the beginning of a critical phase of instability already 2 years before failure, with a good lead time to investigate this landslide better. So I also shown that so this particular method, which is based on part of the INSAR signal, is complementary series. So again, not interchangeable, and also to optical image correlation, and so that no method, I think, can be reliably used for all landslides in isolation, especially in the absence of validation. And so that there is benefit in attempting to develop potential to use other indicators such as interferometric coherence or the rapid phase when we can't reliably return a series of displacements. So I conclude here. Hopefully I didn't take more time.
Thank you so much. It was a wonderful presentation. Taking a look at the chat, we are finishing day 2 of the Landslide Scientific Assessment Conference. Thank you so much, Dr. Benedetta Dini. It was amazing. I also enjoyed a lot how you prepared the slides. Your way of presenting it is very very good.
Thank you.
So, thank you. And so this is the end of the Landslide Scientific Assessment Conference, day 2. I enjoyed so much all the presentations, so many speakers that shared their very interesting research. And I am very glad that we have still day 3 tomorrow. Please take a look at the schedule. We have our social media and the website of the conference, and you will find the information. I was asked by many of you about the certificate for the speakers. We are giving them this certificate as speakers, and for those attending that registered and are participating as attendees, we are preparing a certificate of attendance on the request. So this is what you can know. So feel free after day 3 to send an email to the official email of the conference@landscient.com, and you will receive a certificate. So this is all for today. I hope you enjoyed so much as we did, and see you tomorrow. God bless you so much. Bye bye.